Okay, so good afternoon, everybody, and you're very welcome to the second in the series of highlighting organic chemistry in Ireland. And it's a great pleasure to welcome you. I know it's all virtual, but this is the second in the series developed by the European Chemical Society Division of Organic Chemistry. And it's my pleasure to host this particular event in Ireland. So in terms of Ireland, I'd like to talk to you a little bit about the Institute of Chemistry of Ireland. So this is the national body, all island body for chemistry in Ireland, and it was founded in 1922. So of course, what that means this year, we're celebrating our centenary. So in terms of the council and the members of that, only on Monday, I was elected president of the Institute of Chemistry of Ireland, taking over from Professor Celine Marmion from the Royal College of Surgeons in Ireland. And we also have a new vice president, that's Professor Stephen Bell from Queen's University in Belfast. Emma Coyle is our honorary secretary. Dr. Keegan then is our honorary treasurer. Professor Odila Finlayson from Dublin City University is our registrar. And the editor of the Institute of Chemistry of Ireland's bulletin is Pat Hobbs. You can see we have an international representative, Aurora Walsh, a bunch of ordinary members from across the island of Ireland, and again, very much also highlighted by regional representatives, some of whom are past presidents, as it turns out as well. So they're the council and the officers of the Institute of Chemistry of Ireland for the coming year, and they play a very important role in highlighting chemistry across the island. So you can find out more about the Institute of Chemistry of Ireland at that website, chemistryireland.org. Again, it's the professional body representing chemists in Ireland. One of the key things we'll be doing over the next number of years, in fact, we were due to host the EuChemS Chemistry Congress in Ireland, in Dublin this year, but unfortunately in 2020, the Lisbon 8th EuChemS was postponed for COVID reasons, and they're now having their Congress in August of this year, 2022, so we were pushed back another 2 years. So it's outside our centenary, but we're very much looking forward to hosting that particular Congress, and we would hope to see many of you in person there between the 7th and the 11th of July in 2024. Of course, Ireland is already famous for many different things. And of course, there are some very famous Irish chemists, and I thought I might just highlight three of those. Robert Boyle was born in Waterford in Lismore and is known as the father of modern chemistry. We all know Boyle's Law, but perhaps you did not know that he was born in Ireland. Kathleen Lonsdale, a very famous person in X-ray crystallography and structure determination, born in Kildare, and she was the first person who unambiguously showed that the structure of benzene was flat. Did this by getting an X-ray crystal structure of hexamethyl benzene. Very important lady in the development of structural chemistry. And J.D. Burnell, John Desmond Burnell, born in Neenah. Kathleen Lunsden was born in Kildare, and John Burnell, J.D. Burnell, I should say, was born in Tipperary, and I was born in Tipperary too, so that's the only link we have. But again, he was a very important person in the development of X-ray crystallography in molecular biology. So in terms of the university in Ireland, universities in Ireland, just to give you sort of a broad brush view, there are a bunch. So starting from the top, there's Ulster University, there's Queen's University in Belfast. Then within the Dublin area, there are 4 universities: Dublin City University, Trinity College Dublin, the Royal College of Ireland, University of Medicine and Health Sciences, and University College Dublin. Further south then, in Cork, you have University College Cork. To the west, you've got University of Limerick and also National University of Ireland, Galway. And Maynooth University, shown there at about 10 o'clock on the clock, so to speak, is actually more in the centre of Ireland. So I've shown you where Maynooth is by that red arrow. Very recently then, we've had the development of technological universities in Ireland, and these are very much done by region. So there's a technological university in Dublin. There's the Southeast Technical University, which is a merger of the old Institutes of Technology in Waterford and Carlow. Then MTU is Munster Technological University, which is linking up CI Cork Institute of Technology and Tralee Institute of Technology. Then you've got the Atlantic Technological University, which is linking a bunch of former institutes in Galway, Sligo, and Letterkenny. And then in the centre, the Technological University of the Shannon Midlands. Again, you've a bunch of universities there, again, with Limerick, and I think also Athlone Institute of Technology as well. So in terms of funding in Ireland, the major funders are Science Foundation Ireland, the Irish Research Council, and the European Union. and many of those involved in organic chemistry on the island of Ireland would be involved in some of the SFI research centres. So I'm just highlighting 4 of those here. The Synthesis and Solid State Pharmaceutical Centre, headed out of UL, but with about 9 higher education institutions as part of that. Amber, headed out of Trinity College Dublin, again, very much focusing on materials. SSPC focuses on pharmaceuticals. HURAM is the SFI Research Centre for Medical Devices, headed out of National University of Ireland in Galway. And then BioOrbic, the SFI Bioeconomy Research Centre, is headed out of UCD, but has many members from Trinity and Galway and Limerick and Teagasc as well. So in terms of the biopharma sector in Ireland, very important. It's the jewel in the Irish economy. It's very important perhaps for people overseas to understand that it employs over 30,000 people. It employs greater than 25% of PhDs actually end up in the various industries that you can see highlighted. There you can see some of their logos. It brings in €1 billion in corporation tax. It's responsible for greater than 39% of all of the exports from Ireland. Greater than €10 billion capital investment has happened in the area. The top 10 global pharma companies have bases in Ireland. And in terms of the amount of money, it's €80 billion worth of exports as of 2021. So a very important sector, and that's where many of the graduates from our universities, and again, there's a whole bunch of people that graduated. There's lots of graduate schools in all of those universities I talked about before. So, and the technological universities, and you'd have the size of UCD with about 100 PhDs, Trinity about the same, the RCSI about 55, or 25, I should say, and then DCU in the order of about 60, Galway about 55, and Limerick same number, and Cork would be higher at about 80 to 100 as well. So they have a range of chemistry undergraduate degree programs and a range of graduating classes, typically about 50 to 60, I'd say, per university we could take. So in terms of our speakers today, they're speakers from across the island. Again, starting up north, we've Pete Knipe from Queen's University in Belfast. Then from the Dublin area, we've Donal O'Shea from the Royal College of Surgeons in Ireland, University of Medicine and Health Sciences. Joanna McGuiran from Trinity College Dublin. Stefan Oscarson and Omar Gargle from University College Dublin, and Anita Maguire from University College Cork, and Peter Crowley from the National University of Ireland in Galway. So with that, I'll stop that brief summary of the importance of organic chemistry in Ireland, and I very much look forward to hearing the talk. So if I stop sharing now, I can ask Anita as the first speaker to maybe start sharing her slides now. So hopefully that has been informative, and I look very much forward to the day. And over to you, Anita. Thank you very much.
Can you see my slides there?
Yes, perfect.
Yeah.
All go.
Okay. So thanks very much, Pat, and thanks very much for the invitation to present some of our work here today. You've certainly put together a very interesting afternoon of organic chemistry, and I'm certainly looking forward to the lectures. So I must apologise for giving a very general title. I suppose I didn't decide what I was going to speak about until the last minute, but delighted to have an opportunity to talk with you here today. And the area I want to discuss today is the development of novel methodology employing alpha diazocarbonyl compounds. And these are very versatile synthetic intermediates, providing access to a large range of structurally diverse compounds. Perhaps best known for the cyclopropionation process, where you generate a carbene here from the diazo compound, it adds onto an alkene, and probably the best way of generating the highly strained three-membered ring. The other classical reaction, of course, is the Wolff rearrangement. But diazocarbonyl compounds lead to a very wide range of synthetically useful transformations. So ylide formation, you can have reactions where you actually retain the nitrogen functionality. So in a dipolar cycloaddition, got the aromatic version of the cyclopropionation, which leads to a cycloheptatriene, and probably one of the mildest ways of destroying aromaticity. But the processes I really want to focus on today are these insertion processes. So where the carbene inserts into either a CH bond or an XH bond to lead to the formation of new structure types. And it's a very powerful synthetic transformation. And in particular, what I want to look at today are the copper-mediated processes where a diazo compound here is first of all transformed to a carbene with loss of nitrogen, and then that carbene undergoes an insertion into a CH bond, resulting in the formation of a cyclic system. And here you get outstanding regio control. So the regio control is essentially controlled by the conformation in the transition state for the CH insertion process. So the copper carbene selects one CH bond without any competition from the adjacent position. So that leads to the regio control. And typically you get excellent diastereo control and good enantiomer control in the formation of this new carbon-carbon bond. Now, traditionally, asymmetric CH insertions have been conducted with rhodium catalysts, but I think the advantage of being able to conduct these synthetically powerful transformations using copper catalysts rather than rhodium are evident. You know, the ready availability of copper, the economic advantage of utilizing copper, but also if it's used for the synthesis of a pharmaceutical, residual copper in a product is much less of an issue than residual rhodium because of copper's natural existence in living systems. So over the last 15 years or so, we've been looking very extensively at these enantioselective copper-mediated CH insertions. And I suppose copper bisoxazolene complexes are very widely well known in quite a number of enantioselective transformations. You'll notice our host here identified in one of these reviews, but many of these ligands are now commercially available and they're widely used in quite a wide range of transformations, not just with copper, but also with other transition metals. But I suppose the background for the work I'm going to present to you here today goes back to work from Evans and Fals's group perhaps 30 years ago, where they demonstrated that the copper bisoxazolene catalysts, and particularly using the T-butyl substituted derivative, if you take a 1,1-disubstituted alkene and react it with a diazoester, you get outstanding enantioselectivity in the CH insertion in the cyclopropionation process. And the reason for this is very clear. So the carbene coordinates to the copper, as you see here, and then the alkene approaches it, but the two bulky T-butyl groups direct the alkene in relative to the carbene, and that results in the outstanding stereo control in the formation of the cyclopropane product. So we wondered whether these systems could be used in CH insertions. They were so effective in asymmetric cyclopropionation, could you extend it to CH insertion? And when we started this program of research, there were very few reports in this area. One here from Paul Muller's group, where he demonstrated that if you took this alpha diazo beta keto ester, and you'll notice he uses a very bulky ester here, with copper bisoxazolene ligands, he reported the formation of these cyclopentanones. So you get a CH insertion at this position here to form the cyclopentanones, modest yields, and, you know, reasonably interesting enantioselectivity. But of course, when we looked at it more closely, to get the 60% EE, he had to use the very bulky ester, and he had to use these rather exotic bisoxazolines. If you use the commercially available ones, the enantiomeric excesses were down around 15%. So really, this is a very difficult process. And we suspect that many people had looked at copper-mediated CH insertion and actually not found anything encouraging. So here's our early results. We took a series of alpha-diazo beta-keto sulfones here and looked at the CH insertion into this position to form the cyclopentanone. And with all of the commercially available bisoxazolines, the reaction works very effectively. The CH insertion is an efficient transformation, but the products were essentially racemic. And I suspect that many people had found this and never reported it, that it simply looked like the copper bisoxazolines really don't result in enantiomer control in CH insertion. But then within our research team, one day, Catherine added sodium barf, so Kobayashi salt. And you'll see that by adding 6 mol% of sodium barf to this medium, you get a rapid increase in the enantioselectivity. So certainly a modest enantioselectivity. The maximum value she got was just under 50%, but certainly enough to pique her interest and encourage us to explore this further. So adding sodium barf enhance the enantiomer control of the copper bisoxazolene catalysts. And here you see the pattern. So, you know, we used each of the commercially available ligands, and you see in general you get the best enantiomer control with the indane-derived bisoxazolene, slightly better than the benzyl-derived bisoxazolene, and so on down the group. In all cases, you get the best enantioselectivity when the group here at the site of insertion is a phenyl substituent. So insertion into a benzylic CH bond is favoured in terms of an enantioselectivity. And you'll notice here there's a steric effect. So as you increase the substituent here from a methyl to an ethyl to an isopropyl group, you get a gradual increase in the enantioselectivity, but obviously the electronic effect of the benzyl CH bond overrides this. But you get quite good enantioselectivity and up to about 90% enantiomeric excess achieved in the formation of this new carbon-carbon bond here by appropriate choice of the bisoxazolene ligand. What's significant here is that the ligand trends actually hold up across all of the series. It's not a case of one ligand works with one substrate. We're seeing across all of the series that the same copper bisoxazolene tends to give the best outcome for each individual substrate, and that's useful from a synthetic perspective. It allows you to predict which ligand to use for any individual transformation. So the question we wanted to ask is, what's the role of the sodium BARF in this process? It obviously has a dramatic effect in enhancing the enantioselectivity, but how does it act? And of course, if you think about sodium BARF, the BARF is obviously soluble in the dichloromethane solvent we use, but when the sodium cation is pulled into dichloromethane, it's not stabilized by solvation. It's a naked sodium cation, so it's highly reactive. And we believe what's happening here is that the sodium cation abstracts the chloride from the copper chloride, alters the geometry in the copper complex, so it pulls the bisoxazolene in more closely to the copper and therefore alters the catalytic properties. And in all of these experiments, at the end of the reaction, you see a ring of a white solid, which we believed was sodium chloride, and we actually confirmed it through the PXRD. So we believed that this was the role of the sodium BARF. There was actually the naked sodium cation, which was active here. And we confirmed this. So here we've got a series of investigations when we started with this beta-ketosulfone in the presence of 3 of the different ligands. You see quite a slow process. It took about 20 hours for these to go to completion, and the products were essentially racemic. When we add in 6 mole% of sodium BARF, you notice immediately that the reactivity of the catalyst is dramatically increased. The reactions are now complete within 2 hours, and the enantioselectivities are increased up to 89%. And then the key experiment, we repeated it, but this time we added in 15 crown 5. So of course the 15 crown 5 will complex any sodium cation in solution, and as we anticipated, this reversed the effect of the sodium BARF. So this appears to confirm that indeed it's the naked sodium cation which is key here in enhancing the enantioselectivity in these catalytic processes. Now, we also explored a wider range of alpha-diazocarbonyl compounds. So instead of just having a sulfone group here, we looked at different substituents. So we looked at the ester that Paul Muller's group had used. We looked at phosphine oxides, phosphonates, and indeed diketones. And serendipity played a role here. You can see that across the series, the highest enantioselectivities were consistently seen with the sulfone. So having a sulfone here is definitely favorable in terms of the enantioselectivity. But interestingly, as the electron-withdrawing character of the substituent increases and the electrophilicity of the carbene increases, the reactivity increases, as you can see by the reaction time, almost in line with the electrophilicity. So there clearly is an impact in terms of the electronic effect on the carbene, which is very clear. And we also probed more closely at the role of the sulfone. So we looked at changing the nature of the sulfone substituent. And you'll see with almost all aryl sulfones, you get essentially the same outcome. Slight steric effects, but essentially they're the same. When we simply used the methyl sulfone here, the enantioselectivity collapsed. So that was beginning to point to that perhaps it was an electronic effect and that the aryl ring on the sulfone was somehow interacting with the aryl rings on the bisoxazolene. But the most interesting result is this one here. When we used the cyclohexyl substituent here on the sulfone, the enantioselectivities, they were slightly lower than the aryl compounds, but they were closer to the aryl than they were with the methyl. So it appears that the beta branching here, the branching next to the sulfone, is actually what's critical. So the steric effect of this is critical in terms of giving an enantioselective CH insertion rather than the electronic effect of the aryl ring. Now, so we've shown that we can get excellent CH insertion when we've the sulfone external to the ring, but here we've switched the carbonyl group and the sulfone. So you still have an alpha diazosulfonyl carbonyl compound, but now the insertion has to occur retaining the sulfone in the ring. And again, the copper bisoxazolines are extremely effective for this CH insertion. In this case, the insertion occurs into the CH bond at this position here, so you form the 6-membered ring. The saturated thiopyran is the preferred compound. And you see the enantioselectivity here is even more favorable than in the formation of the 5-membered ring. So the presence of the sulfone in the link, in the chain between the diazo center and the CH bond alters the conformation, because obviously the CS bond lengths are longer than the carbon-carbon bond lengths, and this favors the transition state where the CH bond, which is activated, is at this center here. So you get the 6-membered ring instead of the 5-membered ring. You'll also notice here that the diastereoselectivity is that the cis compound is formed. We get excellent enantioselectivity in the formation of these thiopyran derivatives. And what was interesting here is, again, we looked at varying the substrates. So we varied. Here we either had a methoxyester or a benzyloxyester, or indeed just a phenyl ketone. And we varied the substituents at the site of insertion. So we could have an aryl group, or just an alkyl group, so an ethyl group, or a benzyl group, or an octyl group. And we looked at varying the ligands. And what you see here is that the enantioselectivity in this CH insertion is remarkably robust. It doesn't seem to matter whether this is an ester or a ketone, even though electronically those carbenes are actually very different. And you see the enantioselectivities are best in this case with the phenyl bisoxazoline, but very robust right across the series. So obviously the conformation that leads to this CH insertion is actually it's a very robust one in terms of enantio control. And we've extended this to a desymmetrization process. So if you take this alpha diazosulfonyl ester here, you can get CH insertion into any one of these 4 CH bonds, leading to a different stereoisomer. And the question was, would we be able to get this? Would we be able to get good desymmetrization in this process? And the outcome was, in fact, that this is a very, very selective process. We got 78% yield of this diastereomer here as a single compound, essentially as a single enantiomer. So the desymmetrization is actually more efficient than the CH insertion in the acyclic system. These yields are systematically higher in the desymmetrization process. But the rationalization for this is very clear. When you look at the transition state for the CH insertion, this is the preferred process. So the insertion occurs to this CH bond leading to the diastereomer that we see. If you construct the transition state for the enantiomeric product, there's a significant steric interaction here, which disfavors this interaction. So that rationalizes the high enantioselectivity. And similarly, if you look at the transition states for the formation of the other diastereomers, in each case, there's a disfavored interaction in the transition states, and this results in the highly selective desymmetrization process. So at this stage, we've shown that this CH insertion is very general. So you could have a sulfonyl group at either the internal or the external position, and you could use a range of the different bisoxazoline ligands. So as I've shown with the sulfones, we get the 6-membered ring, and indeed this can be also undertaken with sulfonates. So you can get the cyclic sulfonates in equally efficiently in terms of the CH insertion. If you don't have a CH bond to lead to the 6-membered ring, you can force this to form a sulfolane instead. Again, with good enantioselectivity, not quite as good as the 6-membered ring, but certainly synthetically useful. And here you see that the CH insertion into the benzylic CH competes with the CH insertion to form the 6-membered ring. I've shown you the cyclopentanone derivatives earlier on, and here we've got a case where we take the alpha diazosulfonyl amides, and in this case the CH insertion occurs into the amide substituent, and the preferred ring size is it prefers the formation of the gamma lactams. But once again, if you don't have a CH bond which will lead to the gamma lactam, you can indeed force it to form the beta lactams with good enantioselectivity. And these copper bisoxazolines are obviously widely applicable across a wide range of CH insertion processes, but they're also applicable to other transformations. So here I just show you one example of an aromatic addition. So you form the copper carbene at this position. It adds to one of the 2 faces of the aromatic ring, initially to form this norcaridine structure. And this then undergoes an electrocyclic ring opening to form the cycloheptatriene. And in the azolenone, what you've got here is you've got control of the formation of this quaternary bridgehead stereocenter here with up to 95% EE. So these copper bisoxazolines are actually quite widely applicable across a wide range of diazocarbonyl reactions. Now, many people ask, how do they compare to the rhodium catalysts? And as you can see here, this is one of the rhodium carboxylates that we've recently reported from our group. It's based on the mandalate skeleton backbone. But what you can see here is when you use the rhodium carboxylate catalyst, you can get good enantioselectivity in the CH insertion, but you get the opposite diastereomer. So in this case, it gives us the trans-substituted tetrahydropyran, whereas with the copper system, we get the cis-substituted derivative. And indeed, this carries through into the desymmetrization. So in the copper catalyzed system, we get the stereoisomer where the two hydrogens are cis to one another. When we use the rhodium catalyst, we get the opposite diastereomer. So there's a flexibility here, depending on which stereoisomer you want. You can use the enantioselective copper catalyst to lead to one, or the enantioselective rhodium catalyst to lead to the other. And that's quite useful from a synthetic perspective. So at this point, I think one of the things we often found when we spoke to our colleagues in industry is, well, that's all very nice chemistry, Anita, and the diazocarbonyl compounds, they lead to very powerful synthetic transformations under very mild conditions. All of these reactions typically occur under neutral pH, under mild conditions with very mild catalysts. But there really is a very strong resistance to actually using any of this chemistry at scale, for example, for API synthesis. And that's because of the safety concerns associated with the handling of diazo compounds, both the alpha diazocarbonyl compounds themselves, but even more so their precursors, either the diazoalkanes or the sulfonyl azides, which are commonly used for the synthesis of these compounds. So the Regitz diazotransfer is a wonderful process. In terms of its applicability, you simply take a substrate with an active methylene substituent, react it with a sulfonyl azide such as tosyl using a mild base, and this is an extremely efficient, generally applicable process. The challenge with it is that the sulfonyl azides are impact sensitive, they're potentially explosive. And while there's been a lot of work done in generating safer sulfonyl azides, so the paracetamide derivative or the paradodecyl derivative, these really are compounds that people do not want to use at scale. And these concerns around the safety has really meant that this wonderfully rich methodology is really not considered for large-scale synthesis. So one of the things we wanted to do was to see if we could actually explore how you could bring this chemistry into a sphere where process chemists might at least consider it for large-scale chemistry. And I suppose what really piqued our interest in this was the development of flow chemistry. You can see here, as identified by EuPac in 2019, one of the 10 chemistry innovations that will change the world. And certainly in terms of the way in which APIs are synthesized at scale, the introduction of flow chemistry really is a step change in this area. And we wondered if we could use flow chemistry as a way of making diazocarbonyl chemistry accessible for use at scale. And really the question here is, can you overcome the hazard associated with handling either sulfonyl azides or alpha diazocarbonyl compounds at scale and get all of the synthetic power of using these components without ever actually isolating them or handling them, or indeed having more than a couple of 100 milligrams of them present at any point in time? So what we wanted to do here was we wanted to be able to generate the sulfonyl azide in a flow system, carry it on directly and use it for diazotransfer. So, generate the sulfonyl azide, react it with the substrate and a base to do the diazotransfer. And then the $1 million question is, could you get this clean enough to simply flow it on to an immobilized version of your transition metal catalyst and get the power of the enantioselective catalysis and isolate the product? So you put in the substrate, you transform it through to a diazo compound, and you'd isolate the product without ever isolating or handling any of these hazardous intermediates. So this is a tall ask, okay? First of all, our early experiments in flow, we had generated our sulfonyl azide in aqueous acetonitrile aqueous acetonitrile is definitely not compatible with the immobilized copper catalyst. Simply, you wouldn't get the enantioselective catalysis in that solvent medium, so we needed to adjust this. Leaching of the metal from the catalyst was a huge issue. You could generate the immobilized catalyst in beads and put it into a round bottom flask. That's very easy to do and it works very well. But when you use it in a flow system, the leaching of the metal is a huge issue. So the polymerization to control that took a lot of work. But then the real challenge here is that when you conduct these reactions, you've got a full stoichiometric equivalent of base and you have a stoichiometric equivalent of the sulfonamide byproduct. So when you transfer the diazo group, you're left with the sulfonamide. And both the base and the sulfonamide have the potential to coordinate to the transition metal catalyst. So bringing these through in the reaction stream is a huge issue in terms of enabling the downstream enantioselective catalysis. So this took a lot of work by a very talented group of students. But as you can see on the next slide, we've shown that this is possible. And the reaction I'm showing you here is the desymmetrization process. So we started with the sulfonyl ester, undertook the diazo transfer to form the alpha diazo sulfonyl ester, and then the copper mediated CH insertion to lead to the CH insertion in the desymmetrization process. And indeed, it's possible to do this. You input the sulfonyl ester, you output the CH insertion product without ever isolating or handling the diazo compound. And the key feature here is that the enantioselectivity we achieved using the immobilized copper catalyst in the flow system was exactly the same as that what we achieved if we used a pure sample of the diazo ester and the immobilized catalyst in the flask. The enantioselectivity was not detrimentally affected in any way. So how we did this was we switched to using trifluylazide. Now, trifluylazide is a very hazardous sulfonyl azide. It's not one you choose to use, but if you're only generating it and using it as you're generating it, then that hazard is manageable. And the key feature here is we could generate trifluylazide using a solution of triplet anhydride and toluene and aqueous sodium azide, react them together, and then we simply add sodium bicarb and strip out the aqueous layer. And that removes all of the impurities, the excess sodium azide, the triflate, they're all washed out in the aqueous waste. We then simply run the trifluylazide solution into a flask over KOH pellets, because obviously you don't want water in your metal catalyzed process because you get competing OH insertion processes. So we collect that and then we flow it on to react it with the sulfonyl ester and DBU, allow these to react together for about 2 hours in a reactor coil. And again, we collect that over KOH pellets to complete the removal of water. And then the key question was, would this solution be clean enough to flow onto the copper catalysts? And this here was the magic in the system. The byproducts here, we've got a full equivalent of DBU, we've got a full equivalent of the sulfonamide. Each of those would completely destroy the catalyst. But by passing the reaction stream through silica, then these very polar compounds, the DBU and the sulfonamide, are captured on the silica, and you simply get the solution of the alpha diazosulfonyl ester flowing through onto the copper catalyst, and indeed the CH insertion worked extremely efficiently. And this was almost our first attempt. We isolated a 26% yield relative to the material which we did put in. This wasn't optimized, right? But the key feature is it demonstrated that you can indeed generate sulfonyl azides, undertake the diazo transfer, and undertake the transition metal catalyzed processes without isolating or handling any of the intermediates. So it shows that in principle you can get the power of diazocarbonyl chemistry without actually having to handle any of the hazardous intermediates. And of course, one of the real advantages of diazochemistry and flow is the potential to monitor it by IR. You've got very strong and distinctive bands in a very clean region of the IR spectrum. So if you were using this in flow, you'd simply monitor your reaction outflow. And if at any point there was a buildup of the sulfonyl azide, you'd simply cut off the source of sodium azide, and that removes the hazard immediately. So at this stage in our group, we've done a lot of work in developing distinct protocols for diazo transfer. We now have 5 different protocols depending on the system which you actually want to look at, each of which offers different advantages for different applications. And I won't go through them in detail, but each one of them brings a different synthetic advantage. And I suppose what this is really highlighting is when you conduct a reaction like this in flow, you've got different points where you can control them compared to a traditional batch reaction. and it allows you more control in the process. So we're hoping that this will open up the minds of process chemists to at least consider this methodology for synthesis at scale into the future. Here's another example where we've applied it to the synthesis of Bristol-Myers Squibb clopidogrel, and in this case we were looking at a rhodium-mediated OH insertion. So we generated the diazo compound in flow, passed it through silica gel, and then conducted the rhodium-mediated CH insertion step. In the interest of time, I'll finish there. So finally, I just want to thank you for your attention. And in particular, I want to thank a very talented group of researchers who contributed to this work. Firstly, Stuart Collins, who jointly leads the research team with me. But this is the group of people who've contributed to the enantioselective copper-mediated CH insertion processes. This is the flow group. Each of them have contributed in their own way. And here's our collaborators from UCD who did some work with us in terms of the chemical engineering of the flow system, and the people who've funded our research over the years. And finally, thank you for your attention.
Super, Anita. That's a great start. What a tour de force in asymmetric catalysis, development of really difficult chemistry, getting it out the other end with superb results, and then having the capability to then transfer that into flow chemistry. So thanks very much for that. So again, it's open for questions. And as I'd mentioned in an email to all attendees, please raise your hand if you have a question, and then that gives me the opposite. Pete, you're straight up, so you can unmute yourself. You're a panelist, Pete.
Hi, Pete.
Hi, Anita. Fantastic. Thank you very much. Nice to see you again. I thought that was brilliant stuff, as always. In the copper work, so you find this adding a barf makes your sort of cationic copper species. Do you think does that point to anything mechanistically? Like mechanistically, do you think, is it hydride transfer to form a benzoic cation and trapping back, or is it concerted insertion, or what are your thoughts on that?
Yeah, it's a really interesting question, Pete. One of the fundamental differences between the copper and the rhodium catalyst system is you get competing hydride transfer with the copper catalysts to a much greater extent than you see with the rhodium catalyst, right? So I think the position of the transition state is closer to hydride transfer in the copper than it is in the rhodium, but I think it's not fully hydride transfer. We don't think we're forming the full carbocation, but we do see the products from competing hydride transfer. So I think it certainly is giving us information on the nature of that species and how we can control it further.
Great, thank you.
Great. Thanks very much, Pete. And Virginie,
Yes.
bienvenue, bon après-midi.
Thank you. So thank you, and good afternoon from Paris. A very nice lecture. Thank you very much. I have just a few questions related to your very nice talk. So you demonstrated that you successfully performed the copper catalyzed CH insertion process of different substrate. However, I was just wondering, so you looked at the influence of the sodium barf as well as the oxazoline ligands, but you always perform your reaction in dichloromethane at reflux. So do you observe an influence of some different solvent on the reaction?
Yes, we do. We've looked at that process in a wide range of different solvents, and there is a solvent effect both on the efficiency of the reaction and also on the enantioselectivity and also on the byproduct formation, right? So the solvent certainly has a strong effect, and I think that's because the nature of the copper complex is probably strongly influenced by the solvent environment.
Okay, and did you have a rationalization of why the dichloromethane is the best solvent for this reaction?
I don't think we've actually come to the point of understanding why it's the best, right? Yeah. I think the key feature here, they work very well in toluene as well, all right? I think the advantage of dichloromethane is the ability to have a very low temperature and still maintain reflux. Okay. I think that has a key effect here. We've also looked at higher boiling chlorinated hydrocarbons. They're equally efficient, but the reaction works very well in toluene as well.
Okay, and you perform your reaction using 5 mol% of copper chloride combined with 6 mol% of oxazoline ligand. So would it be possible to carry out the reaction with lower catalyst loading or not?
Yeah, it is possible, right? We deliberately did them at 5 mole% so that we could hold the consistency across for comparison, right? Typically, when we do the rhodium ones, we use much less. You know, we use less than 1 mole%, but we felt that we were better able to hold the relative stoichiometry at the 5 mole% loading. But it doesn't mean that it doesn't work lower than that. It just enabled us to study it more reproducibly.
Oh yeah, and it's very interesting that you were able to demonstrate that by switching the copper catalyst to the rhodium catalyst, you were able to obtain the cis or the trans product. So
yeah,
I was
very
really
useful.
impressed. Yeah, very useful. So
and that's literally because the different nature of the CH insertion. Yeah, one of the big differences actually, if you use copper 1 chloride or copper 2 chlorides, you see exactly the same outcome in terms of enantioselectivity, but the rate of the reaction is extraordinarily different.
Yeah,
and we don't fully understand that.
Right? Okay, so thank you again for this very nice lecture.
Thank you.
Great. Merci Virginie. À la prochaine fois.
See you later.
Yes. Good. So perhaps in the interest of time, we will leave it there. There don't seem to be any further questions in either the chat or the raised hands. So again, Anita, thank you very much for that great start to the day.
Thanks, Pat.
Great. And now our next speaker is Professor Peter Crowley from National University of Ireland in Galway. So Peter, if you want to start sharing your slides, and again, just in terms of the development of the program this afternoon, 3 of the speakers are people who would have represented Ireland at the Young Investigator Workshop over the last 10 to 15 years. So Peter is the first of those. So Peter, your presentation this afternoon entitled Macrocycle Mediated Protein Frameworks. So over to you.
Thank you, Pat. Good afternoon, everybody. Can you hear me and can you see my slides okay?
Yeah, all looks fine.
Okay, so I hope this presentation will go smoothly. It's slightly nerve-wracking giving a presentation online, especially when you have your toddler son in the background ready to make an appearance at any stage. So we'll see what happens. So I'm actually going to begin with an old idea, relatively old idea, and that was the development of synthetic receptors for protein surfaces based on rigid scaffolds with a hydrophobic core and a charged periphery to match a patch or a feature on the protein surface. And you can see this nicely illustrated by Ian Hamilton back in 2003. Many people worked with this concept and developed different types of receptors for different protein surfaces. Here you can see the style of the concept. So we actually started working in this area many years ago. Around 2008, in fact, was our first publication in this area. And at that time, I was a staff member in UCD. So there's an overlap between UCD and Galway here. Okay, so the types of molecules that we're looking at are macrocycles, and we were interested in how these macrocycles might recognize the protein cytochrome C, which is a nice example of a molecular machine. And although our initial interest was in recognition, and what I'm showing you here is a crystal structure demonstrating how that macrocycle recognizes a particular feature on the protein, right? So our initial interest was recognition, but in fact, our research has developed towards protein assembly and the formation of what we call protein frameworks, so porous protein crystals. And here you can see that the macrocycle is really acting like a piece of scaffolding to support the protein in a particular arrangement. This is part of a growing area of an interface, we'll say, between structural biology and supramolecular chemistry. So this kind of host-guest interactions with proteins using different macrocycles and supramolecular receptors. There are many different groups working in it at the moment, and you can see that there are kind of what you might call old-fashioned macrocycles like cyclodextrin, cucurbituril, the calixarenes, and also more recent members of the field, this molecular tweezers from Schrader's group. So a couple of years ago, we published this book. I edited this work, Supramolecular Protein Chemistry, from the RSC. If you're interested, please pick up a copy and have a read. So just to say a little bit more about the main type of molecule that we're going to talk about today, these are the sulfonato-calixarenes developed by Shinkai in the early 1980s. Now, the crucial thing here is this sulfonic acid, which confers water solubility, and similar properties can be obtained with the phosphonic acid, right? So sulfonated and phosphonated calixarenes turn out to be very useful for protein recognition and assembly, while carboxylate calixarenes have so far resisted any real progress. And similarly, cationic calixarenes have yet to really show their promise, at least in terms of crystallization and framework formation. So the interesting thing, or the nice thing about these macrocycles, is their simplicity. And here I'm showing the calyx 4, 6, and 8, obviously increasing size, charge, and flexibility, with solubility actually increasing in the other direction. And, many years ago, Shinkai demonstrated that the calyx 8 arene was a useful receptor for simple guests. Here you can see the trimethyl anilinium cation, right, acting as a guest. And he modestly proposed this suggests that calixarene cavities are capable of molecular recognition. And of course, he meant in water, right? So this was an important development in the 1980s, water-soluble synthetic receptors that could pick up guests in solution. And quite a few years later, it was demonstrated that the calyx 4 was a suitable host to pick up amino acids. So here you can see the crystal structure of lysine sitting inside the sulfonated calyx 4 arene. So as I mentioned, it was about 2008 where we started to look at this type of chemistry, synthetic receptors for protein surfaces. And it was actually some years later before we began working with the calyx 4 arene. And again, looking at cytochrome C as a guest molecule, and I know that's a little bit upside down to refer to a 13 kilodalton protein as the guest, but residues on the surface of the protein behave like guests with the calixarene cavity. And the interesting thing, of course, is that proteins are mobile, flexible. Their surfaces in particular are flexible and dynamic. And the kind of early on question was, well, is any kind of recognition or selectivity possible in this system? And by using a combination of NMR spectroscopy and X-ray crystallography, we were able to show that the calyx 4 arene can bind to different lysines on the protein surface. And we developed that idea of the calixarene exploring by jumping from one lysine to another and kind of roaming around and even camouflaging the protein surface. Now, in a sense, things get significantly more interesting when we work with larger calixarenes, right? So that's our very first result there. Back in 2012, we published that, showing the calyx 4 binding. And much more recently, we moved over to looking at the sulfonato calyx 8 arene. And here you can see just a representative crystal structure with the calixarene binding to a similar patch on the protein surface. Now that might suggest selectivity, but don't pick up that will be a misconception. I'll show you something quite different in a moment. But anyway, let's just look at the series, the calyx 4, the calyx 8, and of course we worked with the calyx 6 as well. And this is an unusual example because in this crystal structure, the cytochrome C has actually substantially unfolded. If we just jump back and forth here, there's a whole loop structure here which changes conformation, and this loop region here becomes disordered, right? So we've substantially remodeled the protein, and that loop that has reorganized is wrapped around the calyx 6 arene. And again, you might think, is it the calixarene? Is that what's doing this interesting chemistry? And it probably is contributing to the altered structure. But another feature here is that the heme group, one of the ligands to the heme, was displaced by imidazole, the buffer that was used in this particular crystallization. Right, so I'm just trying to show you the different possibilities with the different macrocycles, and bearing in mind that crystallization conditions contribute to the results obtained. So why are we so interested in this sulfonated calyxaterine? Well, mainly because it's a flexible receptor. And here you can see different conformations from different crystal structures, just kind of showing off the different possibilities, right? So it can make these little cavities, right? This conformation is related, but the cavity is larger and the periphery is different on each little cavity. In this conformation here, you can see it's actually lost a lot of its symmetry. It's kind of a distorted conformation. And the interesting thing is that, of course, the calyxarine can mold and adapt to the protein surface. In contrast with the calyx 4, which can essentially just grab a single side chain of a lysine or an arginine, the calyxaterine can grab large patches of the protein surface, encapsulating several residues simultaneously. So let me show you what happens when we titrate that molecule into cytochrome C. This is the proton 59 HSQC spectrum of cytochrome C. Each resonance, each peak here corresponds to a backbone amide. So we're essentially observing the protein backbone. And typically, when you titrate in a ligand, you can monitor the changes in the chemical shift of affected residues or resonances, and you can relate that to portions of the protein involved in complex formation. Now, with calyxaterine, what actually happens is at one equivalent of the calyxarine, the spectrum is obliterated. And what that suggests is that large molecular weight complexes have formed in the sample. The sample is it's a perfect solution. It's a true solution still, but the protein is no longer detected, probably because it has aggregated into something relatively large, like a tetramer, for instance. And the really curious result with this particular system, as we add more calyxarine, the spectrum is restored, right? So that suggests that the high molecular weight species has now been disassembled. And if we compare this spectrum with the starting spectrum, there are actually many chemical shift perturbations. So the spectrum is, substantially altered with respect to the pure protein. So what that boils down to, and I'll just very quickly show other techniques that we use to figure out this system, is that we have actually auto-regulated assembly. Depending on the ratio of protein to calyxarine, in particular this calyxaterine, we can switch between the pure protein, this type of tetrameric assembly, this is a hypothetical model of the tetramer here, and also some kind of calyxarine-coated species. So depending on the concentration of the ligand, we can alternate between these species here. And that's actually a naturally occurring phenomenon. Cytokines, for example, they are regulated by the concentration of heparin. They can be switched between monomeric and oligomeric forms depending on the concentration of heparin. So just very quickly, that's the same NMR data that I showed you earlier, just a different representation. These are light scattering experiments here. This is size exclusion chromatography with multi-angle light scattering. So we have confirmed that obviously cytochrome C is monomeric, but when we combine cytochrome C with calyxarine and elute it through an SEC column, we actually obtain a tetrameric species. That was confirmed also by small angle X-ray scattering. Here you can see different crystallographic models and different hypothetical models that were used to interpret the SACS data. Right, so this structure here is a reasonable assumption of what the tetramer is in solution. We also did lots of ITC, or I should say Martin Rennie, the postdoc, did lots of ITC on this system, and you can see that it is, extraordinarily complex. It's not your usual ITC data. Okay, all of that was really just to tell you that you can use calyxarines to assemble proteins to mediate oligomerization. And in some cases, you can have this auto-regulated assembly where you can switch the formation from an oligomer back to a monomer, but actually a calixarine coated monomer. And we're going to return to that idea later, that the calixarine can encapsulate a protein. Wouldn't it be great if we could build little cages around proteins and protect them from the environment? Okay, so moving on now to this notion of frameworks. These are three different crystal forms of cytochrome C and the sulfonated calixatorine, obtained under different conditions. These crystals here are unusual in that you can obtain them with high ammonium sulfate or with polyethylene glycol. And the other interesting feature of these three different crystal forms is that the concentration of the calixarine is important, right? So these forms here, on the left, were obtained at about 1 equivalent of the calixarine, while this crystal form here requires more than 3 equivalents. And actually, the very first structures that we got from these crystals, they were quite difficult to work with. The X-ray data was, it wasn't straightforward to interpret. And later we observed that actually increasing the calixarine concentration to 10-fold or even 20 equivalents, it gave the same crystal form, but with better diffraction properties. Why that is, we don't really know, but it's an interesting point, and we'll see more examples of that later. So just to show you now those three crystal forms, and to remind you again that this calixarine can mold to the protein surface, and it can explore and bind different features and patches on the protein surface. So these are three different crystal structures with varying degrees of calixarine coverage of the protein surface. Not surprisingly, this is the one obtained at 3 equivalents of the calixarine. Right, these are large macrocycles, so they can form large interfaces. This 500 square angstroms here, that's akin to a small protein-protein interface. And in this particular example that we're looking at, approximately 1/3 of the protein surface is covered by the calixarines. So again, this crystallographic result is pointing to the possibility that calixarines can actually encapsulate proteins. Now, to address this thing about frameworks, I need to show you the original crystal structure. Cytochrome C, of course, is a kind of a classic protein. Here you can see the crystal structure from 1990. And as is typical of standard protein crystals, the molecules are closely packed and the protein concentration can be quite high. So in this particular case, the cytochrome C is present at 75 millimolar in the crystal, right? And crystals of cytochrome C, they can be intensely red from the heme. The solvent content, and you're going to see this nomenclature frequently from now on. So SC, the solvent content in this case is 30%, right? And that's kind of their standard values. That's very well known that well-packed ordinary protein crystals, they have a water content of around 30 up to 40%, right? And the protein concentration is high. The three crystals of cytochrome C with sulfonato calixatorine, this one doesn't look particularly porous in this orientation, but it is actually a porous structure. It's 65% solvent, and this guy here is 70%. And the most interesting one is in fact 85% solvent, right? It's a very unusual crystal with an exceptionally high solvent content. And more interesting possibly than all of that is that this crystal form has no protein-protein contacts. The calixarine is the scaffold that enables this crystal to form. Every contact here, every interface is mediated by the calixarine. So let me show you that framework in a little more detail, right? The unit cell here is very handy. It's kind of 10 by 10, what we're looking at here. The concentrations as calculated per the crystal, we have 15 millimolar cytochrome C. We have 3 times that of sulfonato calixatorine, and the ammonium sulfate concentration used in the experiment was 2 molar. Of course, we don't know what it is in the crystal. It's surely not that high, but that's our starting point. And just to prove to you, so as we trot around here through the crystal, you can appreciate how porous that material is. And protein crystals ordinarily are quite malleable or soft. They tend to disintegrate if you're anyway mishandling them. But actually the calixarine mediated frameworks can be quite robust. Not always, but often they are quite robust. Right, and again, that's suggesting that the calixarine is really a glue holding the molecules together. So I'm just showing you again, that's the framework we've just been talking about. And this unit here is the repeating element of the crystal structure. Here you can see some symmetry mates. And I'm emphasizing here the three types of calixarines, the three conformations that are present in the structure. So you can see this kind of opened out conformation that mediates the contacts between two proteins. And this conformation here, the calixarine is kind of folded over on itself, forming two little calyx 4 cavities. Again, it's mediating protein-protein contact, but we've got these little cavities actually pointing out into the void, into the buffer. And on the back of that molecule there's yet another calixarine which is exposed entirely. Well, one side is binding to the protein, but the other side is entirely exposed to the solvent or to the crystal void. And we wondered about, could we do some supramolecular chemistry on these crystals? Well, we've got these cavities, maybe they could pick up guests. That calixarine over there, half of it is exposed. Can it do something different? And we worked with spermine, the tetraamine, and this is actually a really interesting molecule because, well, it's a cation, it's going to be useful for calixarine binding, but it's also structurally analogous to the dilysine motif, right? And cytochrome C has quite a few dilysine motifs that are involved in calixarine complexation. So spermine was a really, kind of cool choice here. And Sylvain Agelberg was a postdoc in the lab. He worked on different co-crystallizations now of protein, calixarine, spermine, and a controlled condition, right? So all of these crystals are obtained under the same general conditions, but with different concentrations of the components. And just to show you one particular type, so that's the original framework, he succeeded in obtaining the same type of framework, but now duplicated. So essentially two Site C calixarine frameworks are merged within the one crystal, and the spermine is necessary for holding that together. Now, in the interest of time, I'm not going to show you the details, but I'd be happy to talk about it if anybody would like to know more. So everything we've looked at so far is with cytochrome C, right? That kind of classic protein. It's a little ball. It's a very asymmetric surface. It's very cationic. And of course, if we want to make our work more broadly applicable, well, not so many proteins are so cationic. Can we also target neutral proteins? And, neutral here we should put in inverted commas because, of course, the net charge of a protein depends on the charge of the solution or the pH of the solution, right? But anyway, if the pI is neutral, could those types of proteins also bind calixarines? And while addressing this question, we were also considering a symmetric target. And the molecule of interest here is known as RSL. It's a lectin. Imberty and Vimerova developed this first crystal structure of RSL. It's a C3 symmetric 30 kilodalton protein. It has only 3 lysines per monomer. You can see them here peeking out, right? So it's quite a different charge property to cytochrome C. And that C3 symmetry, of course, makes it interesting because now you have the same types of binding sites repeated around the surface. Right. And in fact, it has actually pseudo C6 symmetry. This is known as a beta propeller protein. So these little blades here of the propeller, each of these blades is, they have 40% sequence identity. So it's kind of pseudo C6 symmetry within this molecule. So again, we're talking about a ball, but we've got portions of the surface that are essentially repeating as we progress around the ball. That's very different to cytochrome C, which is entirely asymmetric. And just for the laugh, just to show you the type of robot that we use, this is the RX8. We use a commercial Jena screen. And remember I mentioned before about high calixarine concentrations. Well, in the case of RSL, the first results were obtained only with 30 and higher equivalents of sulfonatocalixatorine. So again, Sylvain Angelberg, he developed this project at the outset. He got the first crystals. It was really quite interesting because there was a common theme of very high ammonium sulfate, but a range of pHs, right? And there was also this condition here at lower ammonium sulfate, but only at pH 4, right? And as you'll see, charge, pH and charge are very important in this system. So with RSL and sulfonatocalixatorine, we in fact obtained, again, 3 co-crystal forms. A current PhD student has discovered a 4th co-crystal. That's not fully resolved yet, but we have some more interesting results with this system. But just to highlight how at high ammonium sulfate, this very same crystal form, P213, grows over a broad pH range. So it doesn't matter if it's acidic or basic. As long as the salt concentration is very high, you can precipitate out this protein calixarine complex. And P213, it's not the cutest symmetry. It's not really something that you get excited about, but of course, it's still an interesting structure. It still tells you a lot about what's going on. Now, at the low ammonium sulfate and low pH, right? So this crystal form only grows at pH 4.2 or lower. You get this exceptionally high symmetry and a very rare space group in the protein data bank. And now each protein, each trimer of RSL is coated with 6 calixarines, and the calixarines dimerize to link up the molecules. So let me just show you that in detail. There's the coated trimer. 8 of those trimers pack into the cubic assembly, right? So it's a beautifully symmetric structure and nicely porous, and again, mediated exclusively by the calixarine contacts, in this case, calixarine dimers. We also obtained a crystal form, this time in P3, also at low pH, and this was the curious case of the PhD student who was studying the complex at low pH, Kiefer Ramberg. He left his NMR sample in the fridge overnight, and the next morning he noticed he had crystals. And we said, we better get them down to the synchrotron. And lo and behold, they were nicely porous, right? So that's always a nice day when NMR sample preparation gives rise to crystals, and they happen to be particularly interesting. So again, this crystal form is highly porous, and all of the contacts are mediated by the calixarine in blue there, right? So there are no protein-protein contacts. And this system is particularly nice because now it works at low calixarine concentration, right? That first crystal form requires high concentrations or equivalents, but this crystal form pops up even at low calixarine concentration. Okay, there you can see the 3 crystal forms. You can appreciate these 2 are nicely porous. The interfaces, the surprising feature here is that this combination of valine 13 and lysine 34, this little epitope is repeated in all 3 crystal forms, but the other side of the calixarine complex is a different portion of another RSL trimer, right? So you can see examples of the calixarine molding or adapting to the protein surface, or in this case, this completely flat or depleted loop conformation of the calixarine dimerizing to mediate the interface. I'll just mention in brief, we are working on a system now where a mutation, neither of these residues, but a neighboring residue, when we mutate it, we get a new crystal form with a 3rd calixarine inserted in here. That's really new results that are, we're going to the synchrotron in the next few weeks to develop that further. I'll just hop over this slide, but these are nice cartoons made by Kiefer showing how nucleation is pH dependent. It's dependent on the calixarine concentration. You can grow relatively large crystals within hours. We can take advantage of the sulfur in the sulfonated calixarine to do sulfur SAD experiments for structure determination. So it really is a useful approach to framework fabrication. We also characterize the system, as I mentioned, by NMR. We're down at pH 4.2. It's still perfectly soluble. You can observe the protein. If we go to even lower pH, well, actually, you get a microcrystalline precipitate. So what we're looking at here is just the residual protein in solution. So we can't actually study the system at lower than that pH. If we raise the pH, of course, we can go back to this place. And the surprising result here, so again, we're looking at HSQC regions of the spectrum of RSL. You can see the responses of the resonances to a pH titration in the gray scale and to a calixarine concentration in the blue scale. And the startling result is that, well, the presence of the calixarine gives rise to similar effects as the presence of a proton. How could that be? A proton, the smallest ligand of all, and then this calixarine, which is 1.5 kilodalton, giving rise to the same types of chemical shift changes. That's baffling. At first, at least, it's baffling. But of course, what it means or what it implies is that calixarine binding occurs concomitantly with protonation. And we think that there's a pH trigger in this system. So here you can see the 6 acidic residues of RSL. In black is a pH titration. So we're observing the resonance as a function of pH in the pure protein. And in blue is the protein plus the calixarine. Now, we can't get the entire titration because we'd have to go to too low pH and the system precipitates. But 2 of the acidic residues have elevated pKa values in the presence of the calixarine. And that result is supported by the X-ray. Here you can see one of the interfaces. Those 2 acidic residues are close to the calixarine. So these 2 groups are more easily protonated, which is not really surprising. As you add this acidic ligand, these acidic residues, this one is entirely masked by the calixarine, so its pKa rises. It's easier to protonate that group because it's now buried. This residue actually is the one I mentioned. When we mutate that, we get a new type of interface with 3 calixarines. More on that in the future. And just to finish this topic of the RSL framework, alongside those experiments, we had generated an arginine-enriched RSL where acidic residues were replaced with arginines. And the really startling result was that cationic protein, it has a massive affinity for the acidic calixarine, but actually it gives back the same crystal form. So we get the same, essentially same structure, that P3 crystal form. Here's the original structure with the calixarine kind of masking this protein. In the arginine-enriched protein, the calixarine shifts over. We have the same type of interface, but the calixarine moves over to interact with some arginines. So that's a really unusual result, that we have heavily changed the protein surface, but it still fits into the same framework. The framework is slightly enlarged, but it's essentially identical. Now, back to this idea of encapsulation. Those 3 different crystal forms that I showed you have varying and different degrees of calixarine coverage, right? So here you can see the P213 form, right? The P3 form, and the most beautiful one, the I23 form, right? Now, obviously, these results are based on the solid state. This is within the crystal. But there is evidence to suggest that this also occurs in solution, that the protein can be coated by the calixarine. Now, of course, there are still regions that are exposed, but we do hope to develop this result and, entirely encapsulate the protein within a little calixarine coat, right? And that would protect the protein from the acidic environment, for example.
So Peter, just in the interest of time, are you due to finish in a slide or so?
Oh, sorry, I'll wrap up now in 2 seconds, just to show you thiocalixarine, right? Tie it with the sulfur there. You've now got metal binding, so you can do all sorts of funky stuff. We've just published in Accounts of Chemical Research. That's just out if you want to know more about protein calixarine stuff. I'm going to skip over this. Sorry, Pat, I'm not good on the timekeeping at the moment. That's work that we've been doing with cucurbituril, another great macrocycle. So just to thank the people who have contributed to this work, previous students, current students, and thanks also to the collaborators. I see Alessandro is actually a participant today, which is very nice. I'm really grateful to the Parma laboratory for the collaboration over the years. And thanks, of course, to the funding agencies and to you for listening. Thank you.
Peter, thanks very much. Again, a superb talk, very interesting, supramolecular chemistry. So it's open for questions from the audience. Again, please use the chat function. And I think Alessandro has just done that. So give me a second and I'll find him at the top. So Alessandro, you may ask your talk or question now, Alessandro.
Hi, Pat, and hi, Peter. Thank you very much for a very nice lecture you gave. Very, very, very impressive. Can you hear me?
I can, yeah. Hi,
okay,
Alessandro.
Great.
Nice to hear from you.
Hi. And I have, well, indeed several questions, but I will limit it to few. You mentioned at the beginning that strangely, you never observed any binding with positively charged calixarenes or even carboxycalixarine. Do you have an idea or an explanation of that?
Yeah, so when it comes to anionic calixarenes, sulfonate and phosphonate work really well. The carboxylato calixarenes, I should clarify, we have seen binding in NMR experiments, but we've never managed to co-crystallize a carboxylato calixarene with a protein. Part of the reason probably is that the carboxylate group is, the pKa is not really ideal. So you probably have mixtures of the protonated and deprotonated form, while in the sulfonato case, it's always -1, so it's really consistent, we'll say. With the cationic calixarenes, so actually with Parma, we have tested various cationic calixarenes over the years. They do bind by NMR, and De Mendoza has demonstrated nice examples of calix-4-arenes with guanidinium slotting into C4 symmetric proteins. But all of that work was done by NMR. We have yet to obtain co-crystals of the cationic calixarenes, and I think there's certainly room for development there. I don't know why it hasn't happened yet, but we might be getting there. We'll see.
And if I'm allowed to give another question.
Short question, short answer.
Because you started nicely, you remember the first work done in this field by Andy Hamilton, which was very interesting. And he observed also a change in the oxide-redox property of cytochrome C. Did you ever check that?
A change in the what property?
In oxide-redox properties.
We haven't checked it. I mean, we haven't really done much in terms of function. That's a drawback of our work, I would say.
Yeah. And he explained this by saying that the calixarene was capping the hole of close to the heme, avoiding the entrance of the substrate.
Yeah, like we have repeated those experiments. We've seen, with calixatorine, you can switch off electron transfer to ascorbic acid. It does seem possible that the calixarene is blocking access by the reductant. We didn't actually publish that work, but we referred to it kind of indirectly.
Okay, great. Thank you very much, Peter.
Great.
Thank you very much.
There's a question from the chat from, I don't know if it's Krishna Hari or Hari Krishna, I'm not quite sure, but anyway, the question is, can we extrapolate these systems for energy harvesting applications in the future?
Well, that's maybe a bit of a leap, but I certainly do think that the work we're doing is relevant to biomaterials, using the calixarenes to assemble proteins into robust structures that may form the basis of new types of biomaterials. I'm not sure about energy harnessing, but maybe more biomedical applications rather than energy, for now at least. And
a very quick question for myself. So these calixarenes stick to a protein, and then they have another side of the calixarene that can actually bind to another protein. Can they be selective enough to fish one particular protein out of a mixture of proteins?
Well, that's a good question. Thank you. There's work being done on, this is a huge field. I just gave a very small snapshot, but interestingly, methylated lysines, which are very important in biology, they have much higher affinities for calix-4-arene. And work from Fraser Hoff has, actually 2 different labs have shown that you can use calixarenes to selectively pull methylated proteins out of a mixture of proteins. So there are opportunities there, not necessarily directly in co-crystallization, but purification is actually possible there. Yeah.
Very good. Okay, we'll leave it at that, Peter. Thanks again. And no sign of a child. So all is good.
Thank you very much, Pat.
Okay, you're very welcome. So now we'll pass on to our third speaker for today, Owen McGargle from University College Dublin. The title of his presentation is Coupling N-heterocycles and Organocatalytic Nucleophilic Additions to Nitrogen Heterocycles. So you should be able to share your screen, Owen. Go ahead and do that.
Okay, can everyone see me and hear me?
Yeah, that looks good.
Okay, great. So I've changed the title, sorry, Pat. But maybe I'll start by thanking EuChemS for organising this event, and especially Pat for all the work I know he's put into getting this off the ground. It's lovely to be able to share some of the chemistry from my own research group. And I'm going to start by, if technology will play ball with me, start by thanking that research group, because really I'm just the spokesperson for this group of people who really have amazing talents and work very hard to produce the results that they do, and especially in the last couple of years have really had to struggle against all of the things that we're all aware of to keep things on the road and to keep the results coming out. So today I'm going to start by talking about a project initiated by Vinny and then working with Alex. And then if I have time, I'll talk about some work from Ren and Denicia here and Joe. So that's the plan for today. And just to say, so that's a group photograph from a little bit older. And then also, I'll also mention a new collaboration that we've initiated with Professor Sylvia Draper and Lucas Hallen in Trinity College Dublin. This is the current group. Vanessa is continuing on the project that I'm going to start on now. So I suppose just broadly speaking, my group has a diverse set of interests that are a diverse group of people. But today I'm going to start by talking about some work with organosulfur chemistry in relation to heterocycle synthesis. And then if time permitting, I'll also talk about some of our organophosphorus meets carbohydrate, meets stereoselective synthesis, meets organocatalysis work. So there's a blend of themes going on. So we became interested in bipyridines, and I think everyone probably appreciates that bipyridines are important molecules. There's a few examples here, but it's hard to think of a school of chemistry in the world that wouldn't have some bipyridines in use at some point or sitting in some of their labs for some application. So the thing is that making pyridine couplings is actually not trivial, especially when you want to make unsymmetrical bipyridines. So I've tried to capture on this slide here some of the best methods. So for instance, with transition metal chemistry, which is I suppose your go-to for any aryl-aryl coupling, some of these don't work very well. So Willis actually noted that less than 8% of Suzuki-Miura cross couplings with pyridyl boronic acids give more than 20% yield. And that's a survey of Pfizer's e-notebooks. So some of the methods that you might think would be easy methods to work just really don't. Now, Willis in Oxford has done really good work, so this reference here is probably the go-to for palladium chemistry on this. And then more recent, I suppose, also in parallel the last few years, McNally has done this really lovely work with organosulfur chemistry to access bipyridines. And then while our work was in progress, and actually while we were just getting ready to publish, really, this work came out from the Kin group on sulfoxide chemistry to make bipyridines. And all of these methods are really good. I've just noted on the maybe on the right hand side that they all have limitations as well, as with any synthetic method. So we feel now we've managed to contribute something else that will be complementary to some of these existing methods as well. And how this all started was Vinny Dong in my lab was trying to do an epoxidation using this chiral sulfide with benzaldehyde, so using sulfur ylide, and he tried to generate the sulfur ylide using phenyl lithium. And after a bit of head scratching, he figured out that actually the products of his reaction were not what he was expecting at all. And he had this, he was getting biphenyl and he was getting sulfide. So with a bit of digging around in the literature, he found some, I suppose, relatively old chemistry from Trost and OA that suggested that actually this reaction might be proceeding through a sulfurane. And then he made the connection to work of McNally and others and said, well, maybe our chemistry can add something to this field of bipyridine. So the hypothesis that he came up with was that essentially if we had an aryl pyridyl sulfonium salt that maybe we could react that with an organometallic to form a sulfurane intermediate. And then that sulfurane intermediate would undergo ligand coupling to give this pyridyl to heterocyclic linkage. And so that was our hypothesis. And although there had been work on this that kind of basically preceded most of the work on palladium cross couplings, for a long time ligand coupling had gone out of fashion. But I've noticed that there are I've noted here some recent groups that have been using it to great advantage in the last few years. So it seems like we managed to hit in on an area that suddenly became quite active again. And so to make our chemistry work, the first thing we were going to need was some pyridyl sulfonium salts. And it turns out that actually in the literature, there aren't so many examples of especially diaryl pyridyl sulfonium salts. But even just dialkyl pyridyl sulfonium salts are relatively rare. There's one example from Ritter, and Ritter has kind of showed this really nice applications for sulfonium salts. Generally, there's one example of pyridyls from him. There was some nice work from Arstad and also then Alcarazzo and co-workers as well, where there's been, but I think it's something like less than 5 or 6 examples of a pyridyl sulfonium salt, diaryl pyridyl sulfonium salt in the literature. And again, the synthetic methods out there have limitations. So we set about trying to remedy that. So the first thing was just to do a nucleophilic aromatic substitution to make a pyridyl sulfide. And then we looked for conditions that would be selective for arylation to arylate at sulfur rather than on for instance, the nitrogen of the heterocycle. And if we could do that, we would have access to the sulfonium salts we needed to try the ligand coupling step. So Alex Horan in my lab was the person who then brought this forward and figured out how to get this to work well. And I'm just going to show you a kind of selection of some of her results. So we use this copper catalyzed iodonium salt chemistry to do the arylation. As might be expected, when we tried to do this first, we saw mixtures of arylation at sulfur versus arylation at nitrogen. And thankfully, with a bit of optimization, quite a bit of optimization, Alex managed to arrive at this result. We're using copper, triflate, and DCE. She was able to get exclusive arylation at the sulfur, as best we could tell by NMR at least, in a yield that was useful. And we settled on a loading of 5 mol% catalyst for kind of proceeding with this. And with quite a bit of work, we've now kind of shown that this method is general. And so for 2 pyridyl sulfonium salts, you can make a whole host of them, bearing all sorts of different substituents in different places around the ring. And more recently, we've also added a pyrimidinol example as well. It doesn't work in all cases. So if you try to take a 3-pyridyl or a 4-pyridyl sulfonium salt, you end up with arylation on nitrogen exclusively, and you don't get any arylation on sulfur. And so Vanessa Becker in my lab is working on trying to tackle that problem as part of her PhD, which she just started this year. So now that we had the salts, the next thing to do was to put them into the ligand coupling reaction. And so we started with organolithiums because they're readily available to make the pyridyl lithium species from halo lithium exchange, just using kind of fairly standard looking conditions. So with that, we generate the organolithium, we treat that with our pyridyl sulfonium salt and THF at -78. And we believe we form a sulfurane intermediate, and then what we do see at the end of this is we make bipyridines in quite respectable yields, and we can do this to make 2,3 bipyridines, 2,2 bipyridines with the organolithium chemistry, and we can tolerate quite a few different functional handles. The yields are variable. The method isn't perfect in any means, but it does work, and we can take substituted sulfonium salts and also get decent yields and make lots of different unsymmetrical bipyridines. And I should say that the isolation here is one of the things reducing these are isolated yields, and actually the isolation of these bipyridines from the reaction mixtures is not that is not straightforward, shall we say. It doesn't work in all cases, and in particular that the 2,4-di substitution pattern wasn't available to us from the organolithium chemistry, as well as the fact that some functional groups aren't tolerant of organolithiums to any great extent. So we progressed then to using organomagnesium pyridyl pyridyl nucleophiles, and we found that the turbo Grignard chemistry was the best way to make these. and gave good yields. So we were able to generate them in situ, either from halopyridines or indeed by deprotonation of a CH on the pyridine to make the turbo-Grignard. And we're able to make this work in good yield. And on this slide, I've shown our own results, and I've also shown comparator results. So the magnesium here is our organomagnesium result. The lithium here means this is our previous result for organolithium. In some cases, the lithium is better, in some cases the magnesium. And then where there are comparator examples in the literature, I've also put in details of, say, palladium chemistry, which is sometimes worse, but mostly better in fairness to it, for the examples that where the same compounds have been made. And then also the sulfoxide chemistry from Kin's group, where there are overlaps. Again, I think at this stage we believe that the method is going to be complementary to those other methods. We certainly are better in some cases, and maybe we tolerate functional groups that are maybe not accessible, or substitution patterns that are not easily accessible from some of the other methods. So in particular, these 2,3 bipyridines work very well in our system, which weren't really haven't been demonstrated, at least, to work very well for some of these other chemistries that are out there for unsymmetrical bipyridines. We can also access with the magnesium chemistry the 2,4 bipyridines. So now we have a go-to method for 2,2, 2,3, and 2,4 bipyridines. So especially for instance, library synthesis, we feel that has nice advantages, that you can start from one common precursor and dial in then different substitution patterns. So taking that forward, we've also branched out and shown that this works for other heterocycles. But for the most part, I think many of these other cases are better served. So certainly with more electron rich aromatics, than other methods probably work better. And then we've gone in to look at the mechanism a little bit, and we believe it goes through this sulfurane intermediate. And I might have had that a little bit too small on the previous slides. So you take the sulfonium salt and you treat that with an organometallic, and you get this trigonal bipyridal sulfurane species, and then that undergoes a ligand coupling reaction. And so when we try this with isopropyl magnesium Grignard, we don't see any of the product of the isopropyl group attacking directly here in an SNAOR kind of fashion. So we don't see any of this product here. So that's kind of indirect evidence, I suppose, or a hint at least that the sulfurane chemistry is the way it works. Certainly Trost in his mechanistic studies in OA, where they looked at non-pyridal aryl sulfonium salts, they were able to show pretty convincingly that certainly the sulfuranes are the correct pathway, or the pathway that is followed. So we believe that to be the case. We haven't seen any evidence to suggest it's not. Although we don't fully have an explanation maybe of why when we have these possibilities for other groups to migrate, when we use a pyridal, a magnesiated pyridal or a lithiated pyridal species, that we really only see the bipyridine as the major product in many cases. Okay, so then we've gone on to apply this. We've shown that the method is robust. It works on gram scale. And then we've applied it in the synthesis of these carlamycin antibiotics. So again, just taking this 2,6-dibromo pyridal species, magnesiating that, and then treating that with our pyridal sulfonium salt, we're able to make the bipyridine. And again, here you can see that there's a big advantage in the magnesium versus the lithium in this case. And then formulation brings you to carlamycin E, and then you can make that to the oxime, which is carlamycin A. And so that's the second shortest synthesis of the carlamycins. Duan here has a shortest synthesis, but where we think our method maybe has advantages is the fact that because you have this kind of very modular system, you can then access analogs in a much more straightforward way in fairly short order. More recently, then, we've also branched out into doing some work with material scientists. So Sylvia Draper and Lucas Hallen are collaborators in this, and essentially in a collaboration that happened all over Zoom. I've met Lucas in person once since we started this project, but we initiated it and did most of our collaborative work via Zoom. So they set us the targets of building these bipyridines that have the different linkages on each side, essentially electron withdrawing groups, electron donating groups, and these alkynyl linkers either on one side or the other side of the bipyridine. And without any optimization of our method, Alex was able to take this bromopyridyl sulfonium salt, treat this with the relevant organomagnesium, do the ligand coupling, and isolate sufficient material here to allow her to then take this bromo handle and use standard palladium chemistry, which works very well on when you're not carrying a pyridyl nucleophile into the reaction. So we were able to either do Suzuki or Sonic-Ashira chemistry to make this kind of small a few examples of unsymmetrical bipyridines with these kind of alkynyl functionalities attached to them. And so these were the targets set for us by the material scientists, and now they've taken on those compounds. We've made kind of up to 100 mgs of those for them, and they've been getting some very interesting results, which we are in the process of preparing a manuscript on. And honestly, I'm not qualified to talk to you about the photophysical bit, so I'll leave that for another day for Lucas or Sylvia to do. Okay, so that brings me to the end of what I've jokingly called the first half of my talk. I reckon I'm about 2/3 through actually at this stage. What we have managed to do is we've done this site-selective arylation of sulfur versus nitrogen, developed nice conditions for that, and then shown how you can use these compounds in formation of these bis-aryl compounds. And then we're now branching out into kind of finding targets and applications for those, and finding collaborators for kind of exploiting that chemistry to demonstrate how it can be an enabler for other scientists. So thanks very much to Vinny and Alex. They're the real heroes of this part of the story, and they really are truly great co-workers to have, and they're both progressed now in their careers elsewhere. Okay, so for the last part of my talk, I'm going to talk about something very different. I'm going to talk about our use of organophosphorus chemistry and carbohydrate chemistry in a kind of a combined way. So later today, Professor Oscarson is going to talk to you about carbohydrates, and you'll see for sure, if you're not convinced by my slides, that they are indeed important molecules. One example of some of the carbohydrate-based drugs that are out there is maybe enough to given the time. And what I want to talk about today is just about glycosylation. Stereoselective glycosylation is still kind of a challenging problem in carbohydrate chemistry, and in particular, beta-manosylation is one of the trickier ones that is also one of the important ones. So beta-manosides appear in quite a lot of systems and are not the easiest molecule to make. Some of the best methods are shown here on this slide. So for instance, I suppose one of the most recent ones being this exquisite work from Jacobson's group, where you use these lovely organocatalysts to catalyze beta glycoside formation. So making these 1,2 cis linkages, especially in the mannose case, is quite hard. What's common of all the methods that are on this slide, and indeed all of the methods for this, is that there are always limitations. And in many cases, if you wanted to use these in oligosaccharide synthesis, they're going to place limitations on how you design your oligosaccharide synthesis, because you have to have certain protecting groups in place. So for instance, this benzylidene acetal is a great method, but then means you have to incorporate that into your synthesis, and it has to further downstream steps have to be taken into account. There's quite a lot of work on kind of intramolecular or pseudo-intramolecular kind of approaches. And then also these other methods here that you end up with a 2-OH that's not protected, which is great if you want to use that for the next step, but not so good then if you want to functionalize somewhere else on the carbohydrate. So again, lots of good methods, lots of amazing people have put work into this, but no universal method, and still room for maybe other contributions, which is where we come in. So our source started with this work from Ross Denton, where he developed a catalytic Apple reaction for making alkyl chlorides from alcohols with a catalytic amount of phosphine oxide, which of course reduces the waste and makes your purification much easier. And we were interested in this because the proposed intermediate is this alkoxyphosphonium salt. And we hypothesized that if the OR group here was a carbohydrate, that maybe we could if this was a glycosyl alkoxyphosphonium salt, that we might be able to intercept that species in a glycosylation reaction. And we were hopeful that might be the case because there was existing literature that proposed alkoxyphosphonium salts as intermediates in glycosylations from kind of other starting materials from various groups, Mukayama being, I think, probably the earliest, but then much more later with these kind of POP salts, they'd also been proposed. So we set out to try replicate Denton's method, first of all, and we were able to see that, yes, we could make glycosyl chlorides using a catalytic amount of phosphine oxide. And actually, we didn't even have to do the slow addition process, which would be the normal protocol from Denton's work, where you have to kind of use a syringe pump to gradually add the alcohol and the oxalochloride. Otherwise, you end up with these oxalate side products. So actually, we didn't encounter any of those when we moved to glycosyl hemiacetals as opposed to alcohols as the nucleophile. So then we did publish a paper just showing how you could make all those glycosyl chlorides and how it had a good scope and the method was robust. But then we went looking for these glycosyl alkoxyphosphonium salts. With triphenylphosphine, we really couldn't see that intermediate by NMR, but we were able to if we switched to tributyl. But all of our efforts to intercept this species failed. The collapse of this alkoxyphosphonium salt, glycosyl chloride, seems to be heavily favored. And so efforts to intercept it with alcohol nucleophiles, which are maybe not the world's best nucleophile, failed. So we went back to the drawing board. Before we went back to the drawing board, we did show that you could take the species that you generated and then apply this chemistry from Yi, where you use this urea catalyst to catalyze glycosylations in situ. So you can have a one pot protocol, 2 steps from readily available glycosyl hemiacetals. But then around the same time, this work from Leiden came out from Koday's group, where they had glycosyl iodides, and they were proposing that these alkoxyphosphonium salts were intermediates. So we said, okay, well, maybe chloride is the wrong way to go. Maybe we need to introduce an iodide here. And so Emily Renla Pangener in my group tried to introduce that by adding lithium iodide. So the idea was that we would go from the glycosyl chloride to the iodide and precipitate lithium chloride, and then maybe this species could get intercepted by the phosphine oxide or access the same kind of intermediates as what Koday was seeing. And what she surprisingly found was that in the mannose case, she got beta-mannosides, and that wasn't a result we were looking for at the time. It was just she was trying glucose galactose mannose, and it turned out that mannose rather excitingly gave us these hard to get beta-mannosides. So first of all, just to show, as it turns out, this method has a lot of good scope. I don't want to bore you with tables, but just to say we can access kind of differentially protected sugars at the various positions around the ring. We get high selectivity in many of the cases, sometimes exclusively so, and we can tolerate a good range of protecting groups, but not so much on the ester side. So acetates and benzoates are the major limitation, especially because they're commonly used. But what we do have is a system that doesn't rely on a particular conformational restriction from the protecting groups or some sort of directing group thing. So we think it'll be more versatile in terms of oligosaccharide synthesis and design, in that you get quite active donors, because the benzyl protected donors tend to be more active and more reactive, and you can selectively install a protecting group where you want to then cleave, say, this paramethyl benzyl group in the presence of the benzyls, and that allows you then to have a group that you can just cleave and then progress on to another glycosidic linkage to make oligosaccharides. We also have good acceptor scopes. We can tolerate a fair range of both primary and secondary alcohols, and also even phenols work quite well. We don't get success in every case. Again, the ester formation or transesterification can be an issue when we have ester protected acceptors. We can also do rhamnosides. So we've just, for the non-carbohydrate chemists, we've just switched over from having an oxygen here at the C6 position to having a CH3 group. And again, it shows great scope and works quite well. And again, the beta rhamnosides are also biologically important and also not the easiest ones to make by other methods. Okay, so just to finish then, I just want to say briefly about the mechanism of this reaction. So our hypothesis was that the phosphine oxide was going to be the kind of, the alkoxyphosphonium salt was going to be the key intermediate. But actually, what we found is that's not the case. Our leading hypothesis is just not right. So if you remove the phosphine oxide after this chloride formation step, and then take this glycosyl chloride in with lithium iodide and the alcohol and Hünig's base, you get the beta selectivity. So in fact, the intermediate that forms is not related to phosphine oxide. In actual fact, phosphine oxide can be harmful to selectivity in some cases. We've also independently generated these glycosyl iodides by 2 other literature methods. So this TMSI method from the acetate, or taking a glycosyl hemiacetal with kind of apple type conditions with diodoethane to form the idonium alkoxyphosphonium salt. So we can generate this, we can even detect it by NMR. And in the absence of lithium iodide, you do not get good selectivity. So we get about 2 to 3 selectivity. So you really have to add the lithium iodide. So we can do these other methods and add lithium iodide, we can get back our selectivity. So somewhere in there, the lithium iodide is really helping with selectivity. But what exactly it's doing, we do not know. We've done a bunch of experiments, but we still have more to do to try figure this out. But certainly the lithium iodide is really important in this process. It's not insoluble lithium iodide as well. We've done filtrations where we remove this because there are some insoluble lithium salts present in under these conditions, and we still get good selectivity after filtration. So as long as we don't have the phosphine oxide present. So it might be one of the roles of lithium iodide is to take out the phosphine oxide, in fact, that we were putting in from the start, thinking it was going to be useful. Okay, so what we do have then is what we believe is happening, I suppose, is we believe there's an SN2 reaction taking place on these, I suppose, relatively reactive glycosyl donors, the alpha iodides. By NMR, we can only see the alpha, but there probably is a little bit of beta that can be formed under reaction conditions, which might lead into the minor isomer. But pretty much this equilibrium must be shifted very heavily this way, and we seem to be able to get most of our product to come down this pathway. So this is quite useful then as a donor, this species, because under other reaction conditions you can easily form the alpha monoxide, and then under our conditions you can form the beta monoxide. So it becomes a common donor for either alpha or beta, and again, especially for library synthesis, that's really valuable. Okay, so then just to finish by thanking the people who did the work, so Vinny and Alex in the first part of the story, and then Dee and Ren in the second part of the story. Also to thank Lucas and Sylvia who have been great collaborators. This is the day that Alex got her PhD, Viva. And lastly, just to say, if anyone is interested or knows some talented students, we're currently recruiting for new intake postgraduates. So thank you for your kind attention.
Well done, Owen. Thank you very much. Very interesting N-heterocyclic chemistry, sulfur ligand coupling, and then some really neat glycosylation chemistry. So it's open for questions. Alessandro got in first, and then I'll pass over to Pete. But Alessandro, you should be able to talk. No, he doesn't seem to be able to talk right now, so maybe we'll go straight to Pete.
Hi, fantastic stuff. Loved it, absolutely loved it. In the arylation bipyridine formation chemistry, you're using base acetoxy or a hypervalent iodine species to introduce to form your sulfonium salt. I guess if you wanted to make the process catalytic in sulfur, that would have to be the heteroaryl species, right? And is there any way of doing that? Can you have you thought about trying to make it catalytic?
We've certainly thought about it. Thanks, Pete, as well. Yeah, we've certainly thought about it. I mean, in my past, I worked in the agrowol group, so catalytic sulfide would be a nice thing to be able to do. We've not figured out a way to do it. I mean, you could potentially, I suppose, start from a tripyridal sulfonium salt and be able to transfer 3 pyridines up to 3 pyridines, but we haven't found conditions that would allow us to do the arylations, and
so
we'd have to have a pyridal idonium salt.
That's what I mean, yeah.
And we'd have to have conditions that were compatible with the organometallic as well if you were going to do the whole thing in catalytic form. So it would be nice to do. We're not there yet. And if you have any ideas for how it might work, I'm open to hearing them.
Well, I didn't think that far ahead. Just one other on the actually lower part of this slide. Did you ever try do you know Andy McNally does this trick when he has two pyridines? He treats it with triflic anhydride first to sort of block the less hindered pyridine, and then the remaining one can react in his subsequent reaction. Can you do that here with those bottom ones?
So we've tried to block the nitrogen group in some ways, and what we have tried to do, which is similar to so Andy would take the pyridinium activated pyridinium species by treating them with triflic anhydride, and then treat that with a phosphine, and he has a CH substitution, I suppose, with his phosphines. We tried that with sulfides, and it didn't work. Not at least not to date. But we have tried blocking the nitrogen while trying to do the arylation, but we're still trying that. We haven't figured out a way to make it work just yet. But it is one of the things we're looking at as well. Can we either block the nitrogen, or else can we tune the sulfur by varying the substituents here? And we're doing a bit of both of those at the moment.
All right. Thanks very much.
Great. Thanks, Pete. And Owen, there's a question in the chat from Graham Cumming. Graham, thanks very much. A question on the sulfonium chemistry. Can you perform the halogen metal exchange with isopropyl magnesium chloride in the presence of the salt? If so, this would potentially be interesting in making macrocycles with 2,2' bipyridal, hard to make by Suzuki.
Oh, okay. Thanks for the question, Graham. That's so we have made. We haven't tried to do that. But you're right. If that was that in that particular case, rather than just getting a mess, we might actually get quite useful products. What we have done is we've done sequential. So we've done the coupling. If I go down a slide, we've done a coupling to make say something like this, and then we are this, and then we've done a second a sequential addition of bipyridines, and we've made terpyridines that way, where we've got 3 different pyridines in the terpyridine. We haven't gone as far as making a macrocycle, but if you've got targets you're interested in, I'd certainly love to hear from you, Graham. Yeah.
Very good. Thanks, Graham. Thanks, Owen. Perhaps in the interest of time, we'll leave it there. There doesn't seem to be any further questions coming in, apart from a thanks from Graham on the chat that just came in as I spoke. Owen, excellent presentation. Thanks very much again. And we'll pass over to the final speaker of the first session, if you want to call it that. Pete Knipe from Queen's University Belfast is going to talk on multi-dimensional exploration of conformational space in foldamers. So Pete, over to you.
Thank you very much. Is that showing okay?
Not yet.
Cool.
Yeah, something's happening, and we're there. If you just go on to the full slide mode, we'll be fine. Yeah, perfect. Great.
Perfect. Okay. Yes. Hi. Thank you, everyone. Thank you, Pat, for the invitation to speak. It's been great fun so far, and hopefully it will continue to be so throughout the day. Yeah. So today I wanted to talk a little bit about some of the work that we've done in my group in the area of foldamers, and in particular trying to be a little bit more perhaps creative in the foldamers that we use relative to those that previously exist, some of which are very symmetrical and repetitive. And so that's kind of what I'm going to talk about today. It's about half of it's published work and half is unpublished. Just to show what we do in the group, we tend to split ourselves between synthetic methods, particularly for asymmetric synthesis, and that involves itself with some catalyst development as well. And then across on the other side here, we have some sort of supramolecular type chemistry. And if I'm forced to justify doing all these different things, I would say the unifying concept here is an interest in non-covalent interactions, which are key to basically all of these topics. For those of you who are unfamiliar with the concept of foldamers chemistry, I thought I'd introduce the topic, and as we all tend to do, I'm starting with nature and kind of working back from there. So we're all familiar, I hope, with the oligomers that nature tends to use for function. exemplified by polypeptides. And here I'm just going through some of the functions that are performed. This is catalysis, and this is a decarboxylase enzyme, and you can see the decarboxylation of this position here goes with a 10 to the 17 acceleration in rate, which is, if we were developing catalysts, I think we would be fairly pleased with that sort of a result. So clearly nature is able to do catalysis very well. It also does other things with peptides. So it uses them for signaling. So this is a GPCR transmembrane protein where signals are transmitted across the membrane by a conformational change in the protein shape. And that can go over distances of up to something like 60 angstroms, which is large from a organic chemist point of view. The protein structures are also involved in its structure as well as these sorts of molecular properties. This is spider silk, which is basically a beta sheet aggregate. And it goes with a tensile strength similar to that of steel. Sometimes said to be stronger than steel. It's not quite, but it's in the range there. So clearly, and this is all made from a single set of amino acids, the proteinogenic amino acids, which are just formulated in different ways, and we get all this diversity of function. So obviously, as chemists, we'd like to be able to reproduce to create our own versions of these sorts of materials, and that's where foldamers come in. So I'm talking here about sort of macroscopic versions of mimicry, if you like. So here we have Velcro, which is a mimic of these sorts of burrs that you might get stuck to your trousers if you're walking in the country. You might see, swimming suits the surface of them is low drag, and that's inspired by the skin of a shark. And of course, when we see a bird flying in the air, we like to imagine that we can mimic that through an airplane. Now, this is a silly gif, but it makes the point that mimicry doesn't have to be done in the same way. So a bird can fly. We don't fly in the same way that birds do. And in the same way, I think foldamers chemistry offers the opportunity to obtain some of the function that nature can achieve with polypeptides, but doing it in our own way. So we don't have to do it in exactly the same way nature does it. Just very quickly, some of what's done already in foldamers. So this is some work by Sam Gelman, who really started the field off using beta peptides that form these nice helices. Gilles Guichard in France popularized oligoureas for foldamers, which also form helices and helical bundles, and he's done lots of nice work, catalysis and so on with that same motif. And then Ivan Huck, of course, is again one of the big players in this field and has generated these kind of remarkable. This is a crystal structure. This is a modeled structure of almost 6 nanometers. This oligoquinoline. But what strikes me when I look at these structures is, yes, they're very clever and you can do good things with them. Most of them are helices, and most of them are kind of repetitive helices. And so what I set out to do, and I won't say that we've done this, but we set out to do it, is, can we start to, if we want to start to get some of the function that nature achieves, I think we have to go beyond simple repetitive oligomeric materials that occupy one secondary structure, like a helix. So can we start to generate tertiary structures? And if we want to do that, I think we need to be able to combine multiple domains within a single oligomer, where some regions are extended like a beta sheet, some regions are compact and helical. And once we can start to throw those things together, then we can start to approach the functions that we would like to really get towards. And this is the rationale we had behind the structures we ended up arriving at. So we kind of want, for at least when we start out here, we don't want to introduce too much flexibility, because we want the system to be tractable. So we need some sort of predictable conformational control. We'd really like, if we're starting to think about function, we want to be able to control the disposition of substituents on the surface of our foldamer. So that's what we want to get done. And I also wanted these things to be homochiral. So if we do generate helices, we're not generating racemic mixtures. So, how does structure arise in proteins? This is the undergraduate or even school level chemical biology, which is that we have these tertiary structures which are composed of secondary structures that are thrown together and themselves are built up from primary structures. And something that we observed is that there was a proposal, and it's not necessarily true, but there was a proposal made that this the secondary structures that arise come about because individual amino acids have a propensity to themselves be within a certain secondary structure. So these sort of lipophilic amino acids have a statistical preponderance within beta sheets, whereas these ones tend to appear within alpha helices. And Chu and Fassman proposed that that was because they had a propensity to form those secondary structures around themselves. And so can we think of artificial monomers that would do the same thing, that would, different monomers that would generate different secondary structure types? I said we need to control conformation, and this is the slide about that, basically. We opted to lock the conformation of our oligomers, which you'll see the structure of soon, using this interaction. So we know from work done by us and others that there's a strong electrostatic repulsion effect or dipole repulsion effect between these cyclic ureas and an adjacent nitrogen-containing heterocycle. And that effect is strong. This is, in blue is the rotational profile rotating around that bond if it's phenyl, and you can see there's a 1-to-1 ratio of sort of syn and anti, whereas if you introduce nitrogen, it sits exclusively anti. And we wanted to exploit that interaction. So I said we wanted to generate these monomers with different structural propensities, and this is the design we landed upon. We made a series of 3 different monomer types, all of which are ureas and all of which have nitrogen-containing heterocycles next door, but the nature of that heterocycle is the variable here. And so if we choose to, this was our hypothesis, if we chose to introduce a pyrazine, we reasoned that each of these nitrogens would repel the carbonyl in the adjacent monomer, and that would lead to a particular conformation. Here it leads to the carbonyl here pointing to the left, this one pointing to the right, meaning that these side chains, which are of the same absolute stereochemistry, end up on opposite faces of this sort of linear extended conformation. With a pyridazine, you get a similar effect, but because the nitrogens are on the same side, you end up with the carbonyls on the same side, and these side chains end up on the same face of the molecule. A pyrimidine, we reasoned, would induce a sort of curvature due to the same repulsion effect. And we imagine putting these whole things together into something approaching a tertiary structure, and that's what we're aiming for. Synthetically, these are easy, and I won't belabor this point. You can start from amino alcohol, make an aziridine, open it and close it again with phosgene to get the cyclic urea, and then we couple with this dihalo nitrogen-containing heterocycle to generate a monomer that now has a halogen on here and a protected nitrogen. And then when we build these things up as oligomers, we are doing this in an iterative deprotection coupling protocol. So we remove a nosyl group, which makes this a reactive handle. We couple on the next monomer, and then we have another N-nosyl terminus that we can deprotect and couple as we wish. So it was nice to be able to confirm that the conformations we predicted were the ones that were actually adopted. So this is all the sort of, if you like, dimers, whether this is a monomer or a dimer, I'm not sure. It contains 2 ureas here each, and you can see that each of the conformations are exactly what we predicted. This pyrimidine, I have to be careful with the names of these heterocycles, I get them wrong, induces about a 90-degree curvature in the backbone, and the side chains are all about the same face. The pyridazine is more or less linear. There's a slight bend of about, well, there's a slight deviation from linearity, but they place the side chains on the same face. And then this pyrazine puts them on opposite faces. Okay, so that was nice that we confirmed that this is working. And we also use some solution phase NMR nosy experiments to confirm that that happens in solution phase as well as solid phase. We were also able to show that one could argue in an oligomer, maybe this is only in solution, there could be a lot of rotation happening, and maybe we're not actually getting robust conformational control. The way we confirmed that the conformational control is pretty strong, even in oligomers, is with this tetramer, we were able to see the long range NOE between the 2 termini. And that can only be the case if all of these junctions between the urea and the pyrimidine adopt the conformations we've shown. Anything else would twist it away. And so at least for some of the time, it must be adopting that conformation if we're seeing those NOEs. And we're also able to confirm that this is forms a p helix. Obviously, we've got chiral side chains, and that means that there's a difference in energies between the two helices that can form here. And we were able to, then put these together in heterogeneous motifs where we, rather than having just a bunch of pyrazines or a bunch of pyridazines, we can incorporate different ones and generate relatively complex but very controlled conformations in quite large molecules. And this is about as large as we got at that stage, right? So I'm not going to claim this is a tertiary structure because it's not even long enough to really twist out of the plane. But we have shown that we can create a foldamer where we can control the conformation by choice of monomer, and we can access interesting conformations rather than just simple helices. And I like to kind of think of this as we've built a bunch of these sort of Scalextric track pieces, and we can now just stick them together, and on the back of an envelope, we can work out what conformation this is going to adopt. And that's the work that we published. But we were, we wanted to look at this a bit more. And if going back to that tetramer where we saw the NOE, we did notice that each of these pyrimidine monomers introduces about a 90-degree turn into this backbone. And so we reasoned maybe we can tie these two things together and we can start to make a new type of macrocycle. And in fact, there's work I haven't cited here because it's only just popped into my head, but there's work where instead of this pyrimidine, Otto Meth-Kuhn tried to do this with pyridines and was unable to. And the reason there is clearly, well, we understand now clearly to be that the conformation will never have been right. We know that the pyrimidine conforms in this way. If this were the pyridine, everything would be extended and there's no way the ends would ever come together. So we were interested in whether we could make these things. And obviously, if I'm talking about it, we probably did manage to do that. So I won't talk about the synthesis again. We got to this dimer and deprotected it at both ends so that we have now two sticky handles. And we were able to, using Buchwald-Hartwig type conditions, this then does a monocoupling and then forms the ring with very good yields. So sorry, this represents about 4 different reactions, and the yields here were up to about the high 70s% yield to make the macrocycles here. And these are C2 symmetrical. So we have some control over the sequence of amino acids here. We never made the linear tetramer and cyclized it so that we'd have all 4 different, but we did do that with the trimer. So we generated a dimer, coupled a third monomer on, and these are now all different. And then we're able to close that ring under Buchwald-Hartwig conditions to form the trimeric macrocycle. These are kind of interesting. We have only ever made very small amounts of them. We now have a new way to make them, which means we can start to play around with more applications. But really, that paper just discusses structure and property. These are the nice crystal structures they form. You can see that these tetrameric macrocycles are almost completely planar. That's looking along the edge of that. And they form these back-to-back planes of macrocycles with the side chains extended into the void. So you have these sort of channels in between planes of macrocycles. And even in the solid state, this dipolar repulsion effect is important. It orients these two macrocycles relative to each other between these two ureas. The trimer is a little bit different. It isn't planar because it's too strained. So it has this bowl inversion where the side chains on here favor an equatorial disposition. So these side chains pointing out into space rather than pointing in a sort of axial conformation where they bump into each other. Okay. So that's the work that we've published so far in this field, but we've gone a bit further than that within the lab, and there's stuff I'd like to talk about. So one issue with the foldamer we made so far is if we want to start looking at mimicry or catalysis or anything like that, our substituents are quite far apart. If we're going to start putting functional handles on here, they're quite far apart. If you want to make it, a catalytic dyad or something, is there a way we can put closer together substituents? And one way we thought was if we replace our ureas with diketopiperazines, and now we have 2 side chains that are much closer to each other, and this has the benefit that they're easily made from dipeptides. There's a bit of work in foldamers on diketopiperazines, but actually very little and none exploiting any dipolar effect. So in terms of synthesis, this is very simple. And I will state now that this is the work of one genuinely exceptional MSc student. So all of the work that I'm presenting on the diketopiperazines was done by one MSc student in their 4th year while they were doing exams and everything else on top of it. So I hold my hand up and say this is, you know, entirely to their credit. So that was Sinead McCann. She took these amino acids, did an amino acid coupling with a PMB on one of the nitrogens. And then we could, depending on the protecting group on the terminal nitrogen, if it was Boc, we had to do a acid deprotection and then basic treatment to cyclize onto this ester. If it was FMOC, we could just do all that in one pot. And that cyclized to form this. Now we have 2 nitrogens that are differentially, well, one's protected, one isn't, in an entirely sequence-defined way. And we could then couple with this with dibromopyridine to generate a monomer much in the same way that we've done in previous studies, and start to build up oligomers of these things. So she was able to couple that to this sort of terminal blocking group to generate a monomer, of which we got a crystal structure, showing again the dipolar repulsion effect. Every time we get a crystal structure of these compounds, that dipole effect is in evidence. We've never got a crystal structure where the carbonyl is syn to the pyridine. And then she just said about the iterative deprotection coupling. Here it's CAN to take the PMB off, and then steps of iterative coupling and deprotection. These are nice molecules. So she got a crystal structure of the dimer. If I can make it move. So this is the dimer here. We were a little bit surprised. Everything until this stage was very flat. But what we noticed was that actually at each sort of amide to heteroaryl linkage, there's a slight rotation, a rotation of about 40 to 50 degrees. And it's always in the same sense. So there's always this sort of right-handed rotation, presumably to relieve allylic strain between the heteroaryl group and the diketopiperazine. So there's, you know, it rotates so this CH is pointing towards the heteroaryl group rather than the benzyl group or the ring itself. And we showed through NOSI that this is the conformation in solution as well as in the solid state. So that's kind of, it was unexpected, it's interesting, and you know, it was nice to see that. Sinead wasn't content with this, however. She wanted to push this a bit further, and she wanted to look at dynamic conformation. Of course, one of the things characteristic of natural systems is that they're out of equilibrium, there are movements, there are conformational changes and switches and all sorts of things. So can we, through some sort of stimulus, induce a change in conformation? And what she chose to look at was treatment with acid. So if we treat this with acid, we would expect nitrogen to be protonated. That now introduces a strong, I'm missing a charge here, introduces a stronger conformational control effect. So now the dipole effect is no longer dominant, it's the hydrogen bond that dominates conformation. And so how she did that was she took this dimer and she treated it with deuterated TFA, quite a large amount of deuterated TFA. And amazingly, this was selective for one of the pyridines. I was expecting a mixture, but actually we can show through NMR, you know, the shifts downfield of H2, 3, and 4. Only this pyridine is changed when you add about 300 equivalents of DTFA. The other one is left relatively unaffected. And in terms of conformation, I've tried to make these schematic here. Then if we treat that with triflic acid, you protonate the other pyridine, which is evidently less basic, and you generate a new conformation. But I really like this because I think basically the backbone conformation of the neutral compound and of the dicationic compound are the same. So the backbone here is the same, but all that's changed is it's almost as if we've rattled this thing around and all the side chains have moved around. Right? The backbone's stayed where it is, but the side chains are all in different places. I think that's really, really interesting, and we're excited to put this out there soon. So we're just writing this up at the moment. I've called that dynamic side chain reconfiguration. I don't know if that's an oversell, but I think it's interesting nonetheless. Sinead then also wanted to look at side chains where we could introduce some function, right? Everything so far has been quite lipophilic, just bits of grease that will help us purify but won't have any interesting function. But once we introduce things like acids or amides or amines or something like that, we can start to, make ureas and make all sorts of things that might do catalysis. And so she attempted that with this glutamic acid derived diketopiperazine. And what we found, which is kind of strange, is that when we do the coupling with these, remember the base here is cesium carbonate, when we do the coupling with these, we tended to get mixtures of diastereomers, which we hadn't seen with the other monomers. And we get this at every stage. So somehow, and it's, I will point out that there are at least 5 diastereomers when we take the major out of this dimer and couple it to make the trimer. So the implication is the presence of this monomer anywhere in the molecule induces epimerization not only at proximal to it, but actually everywhere, which I don't understand. And if anyone has any clever ideas, liberation of terpbutoxide, I don't know, why would this being here affect epimerization over here? I really, I'm not sure about that at all, but it's something we need to look at. There's some work out there on different palladium catalyzed conditions that minimize epimerization. So we're gonna work ahead on that, although Sinead's not finished. So the last thing I'm going to talk about is all of the oligomers so far have been a sort of backbone where we've been able to control the conformation in the XY plane if you're looking down on it, right? So we've been able to, and we've been able to put substituents above or below, but we've never been able to put substituents out to the side. And that's a limitation if it comes to, again, catalysis, mimicry, anything like that. I'll put that in terms that it makes sense to me. If you're going along the axis of the foldamer, until now we have control of yaw, right? By changing the nitrogen substituents, we can turn the backbone in different directions, but we haven't yet had control of roll, right? We haven't been able to twist the overall conformation or the overall backbone along the long axis of the foldamer. And that's something then that another student, Will Rowe, has been working on. And we thought we might be able to do that by introducing, again, replacing our urea component, but this time replacing it with a spiro bislactam, which should rotate the overall axis of the, rotate the long axis of the foldamer by 90 degrees and then allow substituents to go out along different vectors. Synthetically, that's a bit more difficult, but it is possible. And I apologize, I should have a citation for Darren Dixon's work here. So this work here mirrors some work by the Dixon group in Oxford. They, using an asymmetric phase transfer catalyst, used these, I forget the name of this species. It's amino alcohol derived, but it's basically behaves like a tosylate, so you can alkylate and displace the oxygen here. So forming the enolates of these under phase transfer conditions leads to alkylation to form the quaternary center. We did it with achiral phase transfer catalysts. We got an okay DR. The DR wasn't that much better with cinchona alkaloid derived phase transfer catalysts anyway. So we generate our quaternary center, then treatment with TFA and coupling conditions close this Boc, nitrogen is deprotected and cyclizes onto the tertbutyl ester to form our bislactam, now differentially protected at either end, and with the stereochemistry of the spirocenter controlled by the amino alcohol that we used to start with. And then we chose the pyrazine as a linker for this, so we now have a monomer. And we then set about the business that we've done on the other projects that I've presented, where we build this out into a longer oligomer to look at the conformation. So coupling under very similar conditions generated this sort of monomer, and we were able to, NOE didn't help us much here. There's a lot of congestion here. We wanted to know the absolute configuration of this spirocenter. We knew obviously that because we bought it, right? We knew it was naturally derived phenylalanol. So we knew this stereocenter, we didn't know this one until this stage where we got a crystal structure, and that gave us the absolute and relative to the benzyl. So we then took that forward. None of this chemistry works when this is nosal. We'd used nosal before because it's very easy to take off with thiophenolate. When you make this tosal, the reaction the sequence works up to this stage, but then you have a deprotection issue. I don't know if anyone's ever worked with tosal amides. They're not the easiest thing in the world to take off. I can see you popping up, Pat. I'm going to be about 2 more slides. So we had a lot of trouble with this, and basically the student. So I'll not go through this. You can see all the things we tried that didn't work very well. Samarium iodide worked pretty well, but we had trouble handling it, and it goes off very quickly. In the end, what we ended up using was, well, the student went away and tried dissolving the starting material in sulfuric acid, which I never would have recommended in my life. I didn't even know that took tozal groups off, but apparently it does. And then we refined that a little bit, and triflic acid and DCE takes this off quite cleanly with no epimerization and very little problems. It's very clean. So then we were able to now build this thing up, and we're now able to couple and deprotect. And you can see now I'm drawing here the rotation in the plane. So this segment is perpendicular to this segment, and then we get another rotation, and at each monomer we rotate along the plane. And so we can build these things up, and I've given the yields for each of those steps. And then we even cheated a little bit and made a hexamer by taking the trimer and coupling it twice into this dibromopyrazine. So you make a back-to-back trimer. And in terms of conformation, we only have crystal structure of the monomer, but the modeling agrees with the crystal structure, and so we take that on to the higher order oligomers. And so the conformation here, you can see that's the monomer, then the twist happens, and there's the dimer, then another twist, and the trimer then is back into the same plane as the first one. And then the hexamer has this really long helical conformation, where this is a helix with a pitch of about 32 angstroms, which I don't know of anything quite like this. It's quite strange. And looking down the barrel, it's kind of like a helix, it's like a boxy helix where you have walls that are 90-degree oriented relative to one another with a sort of square channel down the middle, which I think is really, really interesting. Lastly, we're able to show that this is now compatible with the earlier work with urea-based monomers. So we're now building up a picture where we have all these different intercompatible chemistries, all using the same sort of couplings. So in theory, we could start to put these all together and build quite complex, sort of something approaching tertiary structures. So I'm going to wrap it up there and just finish by thanking the people involved. So so Zach Lockhart, who then worked for Martin Smith and is about to go and do a postdoc for Macmillan. He did the initial work in the first work I presented. Toya did the macrocycles. Sinead was a master's student who did all the diketopiperazines, and Will has been the one doing the spirocycles. Thanks to everyone for funding. Thank you all for listening, and I welcome any questions. Oh, and we've got 2 postdoc positions available in the summer, so please get in touch if you're interested.
Good, good. Why not get the advertisement in while you can? Good. Pete, excellent presentation again. And Joanne, you have a talk, or a question, I should say. You will have a talk later, but now you have a question.
Yeah, thanks. Really nice talk. It was especially interesting to see the sort of acid responsiveness of some of your units. I was wondering if you see any differences with the conformation if you just change the solvent.
Very little, you know. So I didn't really get into it, but part of the when we're trying to deduce the conformation in solution, the only handle we have is the NOE or lack thereof between that CH there and the benzylic one here, or the CH here. And if it adopts the conformation we expect, that should be very, very weak. And we tried to quantify that a bit. If it were to turn around, that would start to be a strong NOE. And what we thought was if we stuck this in DMSO, you'd reduce the dipolar effect relative to the solvent would then compete, and you would start to see a much stronger NOE. We basically found that even in DMSO, this thing adopts the same conformation. So the repulsion effect is very strong, and it holds up almost regardless. We've never really put it in a protic solvent because the solubility becomes an issue, which would be interesting because you'd introduce hydrogen bonding as a competing factor. But certainly in anything polar aprotic, it's the same.
So it seems like it's really just locked in that conformation.
Yeah.
Cool, thank you.
Great, thanks, Joanne. Actually, Pete, just a question for myself. I mean, some of the stuff at the very start where you made those sort of macrocyclic polymers, having listened to Peter Crowley's talk earlier, it seems like they have that type of functionality that might allow them to maybe bind to proteins.
They bind cations. We did show that, actually. I didn't have time to talk about it. In fact, I've spoken to Peter before about this, and I think we could maybe reignite that interaction. So yes, it's a very good point, Pat. Thank you.
Yeah, no, great. Hopefully that will be useful. Now, I don't see any other questions coming through either with raised hands or in the chat. And we're at exactly 3:30, which from the schedule should have been a coffee tea break. So perhaps if it's okay with everyone, we might take a 10-minute break here. And our next speaker, which will be Stefan Oscarson, will start at 3:40 Irish time, 4:40 Central European time. So if you're worried about all of that, 10-minute break, that's it, and we'll start again if that's okay. So I'll just pause the recording there. Okay, so our next speaker is Joanna McGurran from Trinity College Dublin. Joanna, are you ready to share your screen?
So hopefully, can you?
That looks fine. Just go PowerPoint and fingers crossed. Start.
Can you see the slide now?
Yeah.
Great.
Good.
Okay. So thanks so much for the invitation to talk today and tell you a little bit about what my lab are working on. So one of the things we're really interested in our lab is DNA damage repair and the pathways involved in this. One of the most toxic variants of DNA damage repair is interstrand crosslinks. So if you glue the two strands of your DNA together, then you completely block replication of your DNA or transcription into any proteins. So our cells have come up with ways to combat this type of DNA damage, and this is quite a complex set of pathways, but one of the key players in here is SNM1A. So this is an exonuclease, and what it does is it comes in partway through the pathway and it will chew down a strand of DNA from the 5' end to the 3' end, releasing one nucleotide at a time. And it will do this past any crosslink that's in its way, and then we end up with one strand of DNA which can go ahead and be repaired. So this is critical for healthy maintenance of our DNA, but it can become problematic because DNA cross-linking therapy is often used for hard-to-treat tumours. And so if the DNA repair pathways can come along and just repair this, then it stops the therapy from working. So being able to look at the activity of this DNA damage repair gives us a good idea of how effective cross-linking therapies are likely to be, and also we could potentially inhibit the DNA damage repair pathways, and this would make the cross-linking therapies more effective. So they're really important enzymes to be able to study the activity of. And so to look in a little bit more detail, SNM1A has, it's a metalloenzyme. It's thought to have 2 zincs in its active site. It also requires a 5' phosphate for recognition of the substrate, and then it has a long patch of DNA recognition as well on the enzyme. And these 2 things work to present that first phosphodiester bond in the active site, and then this can get hydrolyzed by the enzyme. It releases one nucleotide, and then we have an oligo substrate that's one shorter, and so this can keep being chewed up by the enzyme. So the probes we'd ideally like to make for this are shown here in the bottom right hand side of the screen, but these are quite ambitious to try and make. So these mimic the substrate, and then we would put in the place of a cis-al bond something that can't be cleaved, and ideally could also stabilize the binding interaction to the metal center, and so this would give us specificity. And then ideally we want as well some way to characterize what we've bound to, possibly pull it out. So this is what we'd be aiming for eventually as our final goal, but these are quite tricky to make. So we thought we'd kind of break it down into more bite-sized chunks and figure out what bits we need within our probe to make it work. So today I'm going to focus a lot more on looking at the monomers and a few dimers and how well these will bind to the enzyme. So if we get something that has good binding, then we have, I think, a good chance of incorporating that into an effective probe molecule. So we started with the simplest version that we could. So to start off with, we looked at just modifying the 5' position, and for this we use thymidine as our base in every instance, because here we don't have to protect that, so it just simplifies our synthetic strategy. Each of these was straightforward enough to make in under 10 steps from thymidine. I'm not going to go through the synthesis all of them, but since this is a more organic focused talk, I thought I'd take the opportunity to go through a couple. So to get the, actually also just to say a lot of them are based on hydroxymic acids, which are known to be good zinc binding groups, but because we had in our minds that eventually we want to make these much more elaborate structures, but we were quite interested in if, instead of just using a hydroxamic acid, if we could potentially use that kind of motif but incorporate it into something that would be bridging, which is why we have these kind of alkylated hydroxamic acid motifs that we were also interested in. So in terms of making compounds 2 and 3, we started off with our thymidine, did a Mitsunobu type reaction and deprotected, and that installed our nitrogen, and then we could go ahead and just do an amide coupling, deprotect, and that took us through to our first targets in a reasonably straightforward manner. We then went on to put together the hydroxamic acids, and again we started off with protecting group manipulations to give us the free 5' position. We could then oxidize that, and again from the carboxylic acid we could then do a coupling. So in this instance it's to take us through to the hydroxamic acid, but we also got through to a lot of the variants using a similar strategy. So these all work pretty nicely. We also did a slightly longer hydroxamic acid, so the original one would be slightly shorter than we'd ideally want. And so with this, we did a Wittig coupling and hydrogenated to get us through to carboxylic acid. Again, we could couple, and this one very nicely gave us the longer hydroxamic acid. So this is a 2-carbon extension. So we would also be interested in the 1-carbon extension, and we put a lot of effort into this. I'm not going to go through quite all of the things we tried, but this was kind of the closest we got to the 1-carbon extension, which was again starting from this aldehyde. We went in and we introduced this dithioacetal motif. So we found already with this that we were starting to get epimerization at the anomeric position. This seemed to be pretty slow that it was happening, so we could actually separate out the diastereoisomers. So it gave us a terrible yield, but we had enough that we could get through to push through to get through to the ester. Unfortunately, we found once we got through to the ester, hoping to carry on, get through to our hydroxamic acid, that also the ester was doing something similar. So again, we were getting these ring opening products and we were getting epimerization. And we reasoned at this point that possibly any time that we put a carbonyl in at this position, we were quite likely to see this issue. And so this is why we end up with the kind of 0 and 2 in our series of the hydroxamic acids, and the 1 is missing. And we went through, we made the rest of the targets, and again, they were reasonably straightforward to make. So in the interest of time, I'm going to not go through quite everything. And then once we had our small panel of potential inhibitors in hand, we went through and we incubated those all with the enzyme, and then we treated with a substrate which has a fluorophore on there. And then essentially what we'll see is if we run the DNA itself out on a gel, a DNA gel, if it's full length, we'll see it at the top of the gel. However, if the enzyme has digested it, so this is where we don't add any other potential inhibitors into there, then the DNA has got a lot shorter, and so it runs much further down the gel. So what we did was we put the rest of our inhibitors or potential inhibitors in. And as you can see, most of them, the DNA has been digested similarly to if we didn't add anything. And so most of them actually aren't really binding to the enzyme at all. However, we did find that the 2 hydroxamic acids were, anytime when we tried to use the hydroxamic acid as any kind of bridge, our activity really dropped off. So we found that that strategy wasn't going to be a good long-term plan, which is nice to find out early. Also, we were interested in a couple of squaramides as well as phosphate bioisosteres. But again, we found in this instance that we couldn't see any binding from those either. But the 2 hydroxamic acids were great, so we took those on. We looked a little bit further at their activity. We found that whilst they did inhibit, they weren't fantastic in terms of potency. So we got an IC50 of about 140 micromolar. So it seemed like we had a little bit of optimization to do, but we were kind of happy enough that we had a good starting point with this. So the next reasoning we had for our next set of molecules was that we have these two metals in the active site, and we were, with the hydroxamic acid, we were quite possibly only effectively really binding to one of them. We thought maybe if we moved to a malonate type structure, we'd have the potential to bind both of those metals, and so we could hopefully increase our potency of our binding. And at this point, we were interested. The other nice thing about the malonates is we could potentially use them as a bridging structure as well. So now we were interested in putting them on the 5' position and the 3' position, as well as using them to bridge onto dimers. So in terms of putting those on, we first off generated a good leaving group at our 5' position. We also now at this point we do have to protect the thymidine, although we'd got away with it in the first round. Conditions now a bit more forcing. So we protected our nitrogen there as well. And then we could install our malonate at binding it through the central carbon here. So then we could go through different protecting group manipulations, and that could take us through to different variations of our malonate. So at this point, our initial strategy was again to make the carboxylic acid and then do an amide coupling to install the hydroxamic acid moiety, protect it and then deprotect it. We had up until this point quite a lot of issues with doing this. We found that those amide couplings were quite fickle, so sometimes they work reasonably well, other times we just couldn't get them to go at all, and they seem to be very sensitive to sterics. So at this point, we actually swapped to doing an aminolysis. So starting from the methyl ester, which in this instance we had anyway, but in other instances we would generate, and then doing the aminolysis reaction. In this instance, the yield was actually pretty terrible, but we generally found that we could get much better yields and much more reproducible results as well. So we switched to that. As well as putting the malonate on through that central carbon, we could also attach it kind of onto the end. So we went through and did this. Again, this worked quite nicely, and the yields we got were pretty good, so we could get through those targets with relative ease. The other thing actually that we found, I should mention, as well as the issues with coupling the hydroxamic acids, is originally we'd used benzyl protection, and we found that the deprotection with the palladium on carbon, the hydrogenation, often we had real issues with purification. And we think a lot of the issue with that was essentially when we generated the hydroxamic acid, that was also acting as a pretty good binder for the palladium. So getting it off and getting it clean was an issue. So again, the aminolysis, because we don't have to then do the hydrogenation, seems to be very helpful for this. So that was putting them on the 5'. We got through to quite good routes for all of the targets that we wanted. When it came to putting it on the 3', we were interested to be able to do the 2 variants as well, but we found actually that attaching it via that central carbon, if we used conditions forcing enough to get a reaction, then actually the products that we were getting were just the elimination products. We could also get the hydrolysis product, but again, we weren't too excited about isolating that. So again, we knew we were making the nucleophile because we've been using it in the previous reactions. And I guess we know we can get this mesylate to leave because we were getting the elimination, but to get that substitution, we had, again, real difficulty. Luckily, putting it end on the 3' end again, worked quite nicely. So we could just start with AZT, which is commercially available, and then again, just go through an amide coupling route and then the protecting group manipulations that we wanted. And so we got access to to these targets. We also went through, and again, this is mostly kind of protecting group manipulations to get through to the dimers. So because we were limited to the amide coupling for getting it onto the 3' position, we made dimers of this configuration. I should also mention as well that we have mixtures of diastereoisomers because the proton here is very labile. We figured in terms of the enzymatic assay, because this interconversion seems to be really rapid, and also the configuration within the active site is quite likely that we could well see that proton being lost anyway. At this point, we weren't too worried about the fact that we had the mix of diastereoisomers. We just took them through and screened them as they were. And so this is the results of this series of compounds. So you can see the 5' ones that were linked by the carbon. These all look pretty good in terms of the inhibition. So we're getting a decent amount of binding there. If we link them kind of end on, then actually these looked much worse. The ones on the 3' end looked better than the ones on the 5' end. And now that you can pull them out a little bit, you can see that generally from each series, the hydroxamic acid one looks to be the most potent of them. And then if we made the dimer, this certainly seemed to be better than just the corresponding 3' end, but maybe not quite as good as just the corresponding 5' end. So we then took our most promising compound forward. Again, we diluted it to slightly less forcing concentrations. We could see that although we did get a decent amount of binding, it wasn't actually as potent as our original shorter hydroxamic acid. So although I think the idea had been quite elegant, it turns out that the binding wasn't where we needed it to be. So although we didn't get our significantly more potent binder, we did learn quite a lot along the way about the 5' linked versus the 3' linked. And then also the dinucleosides, and also where we positioned the malonate, as well as the modifications we put onto it. So we weren't quite ready to give up on the idea of just kind of adding some extra binding to potentially catch those two metal ions. So we went back actually to our square amides, and this is quite a nice system because we can essentially just bolt. If we start with an intermediate like this, we can substitute at this position very easily and put different things in that could potentially give us some extra binding. So we made a small panel of these. We tried them, none of them seemed to do anything at all, which was a little bit discouraging, but we weren't going to be put off that easily. We knew from the malonates that if we put things at the 3' position, we generally got better activity than putting it at the 5' position. So we went ahead and made a series of thymidine derivatives where we put something at the 3' position, and we found that if we had the N-hydroxy group on our square amide, we could in fact see some level of inhibition, and also if we had the squaric acid. So why we'd originally avoided doing this is it's then going to stop us from making an oligo chain if we're putting our modifications at the 3' position. But we reasoned if we could get away with using the corresponding RNA rather than the DNA monomer, then we have that 2' OH. So we have the possibility then of still incorporating these into more complicated structures. So we went ahead and looked at the uridine derivatives, and we saw that although the inhibition wasn't quite as good, we do still certainly see something for the uridine variant. So this would be a way that we could still incorporate them into more complicated structures along the way. We also looked at this point at thiosquaramides, so we thought if we could put a sulfur in place of the oxygen, we'd probably get much better zinc binding. Interestingly, here we saw our trends were reversed from what we'd kind of previously been seeing. So these are certainly, the 5' versus 3' is certainly a trend rather than a rule. So here the 5' was the most potent, the 3' was intermediate, and actually the dimer was the least potent variant. So I saw these as we kind of build up a set of expectations. We have to always take them with a pinch of salt because not everything's going to follow them. The other very nice thing about the squaramides is because of their aromatic nature, we could actually correlate, we could examine their zinc binding ability, and we could correlate this to how good they were as inhibitors. And so we found, again, more of a trend than a rule for sure, that things that tended to bind zinc better were also more likely to be a better inhibitor of the enzyme. So I think with this, what we can take away from it is if it's good at binding zinc, then we have the potential to make it into something that could be a good inhibitor or a good probe. Whereas if it's not good at binding zinc, we're probably not off to a fantastic start. So again, we got a lot of helpful information from this along the way. Again, unfortunately, we still couldn't crack into making something significantly more potent. So again, we were gathering more information, but not necessarily getting down to something that's going to be a fantastic binder for the enzyme. We then went ahead and looked at some alternative zinc binding groups. And these ones, again, we saw maybe a little bit of binding with some of them in our enzymatic assay, but none of them looked super duper promising. So at this point, we thought we should really consider our strategy. We went back and we thought about the enzyme and what it's doing and how it's binding things. And this is just a cartoon. As there aren't really any crystal structures bound to the substrate, but we knew that we needed this 5' phosphate for enzymatic activity on oligonucleotides. So it stands to reason that there is some kind of binding interactions if you have a 5' phosphate. Otherwise, how would it be required for the activity? So that led us to think, well, you know, now that we've moved on to generally putting our zinc binding groups on the 3' position, we have a free 5' OH. If we phosphorylate it, what will happen? So we went ahead, we made a few different phosphorylated variants. I should also mention again, so we just phosphorylated uridine as well. So always we've just put the unmodified base in as a control. We never see, sorry, excuse me. We never see any degree of binding just with the unmodified base control. We thought because we're phosphorylating it, we should put the phosphorylated nucleotide in as well, and then have a look in the assay. And we were delighted to see that actually everything that we phosphorylated was now giving us a significant degree of binding and therefore inhibition in our assay. Actually, we saw everything, including the phosphorylated uridine. So we went ahead and got the IC50s of these, and you can see that actually just the phosphorylation itself is already pushing us down, and we've cracked that kind of 100 micromolar barrier that we were struggling with before. But it was really nice to see that actually adding a zinc binding group does help out. You can get into get more potency by putting those in. So these were the uridine analogs. We also went ahead and made thymidine variants as well. Again, just the phosphorylation of the thymidine already is pretty potent, but we can push this even lower with the different modified squaramides, and we see a difference between the different zinc binding groups. So just in summary, we are, I think, very excited about being able to get towards something where we can make an elaborate probe scaffold, and we can look at the enzymatic activity, not just with the recombinant enzyme, but in a more native environment. And we're not fully there yet, but we're definitely on our way, I think. So we've looked at a lot of different zinc binding groups. We've been able, in some instances, where we can look at the UV to correlate the zinc binding strength and the inhibitor potency. We've looked at thymidine versus uridine. Thymadine's better, but we can get away with the uridine. We've looked at the 3' versus 5' in terms of where we put the modifications that we want to introduce. We found generally the 3' is better, but then we have to consider what kind of linkages we'll make. The monomers versus the dimers, again, we found generally the dimers better, but depends on your dimer. And we found that actually universally with everything we've tried, the phosphorylation has really, really helped. So that's very encouraging. And I think then if we can start to elaborate these with long oligonucleotide tails, then we can get into something that will be significantly more potent. So I'd just like to thank my group who did all this really exciting work. And so specifically with this, Eva and Mark, who are handily stood in the front of this photo, who are two of my first PhD students, and then William, the group's first postdoc, who between the three of them did all the work that I've talked about today. Also, the rest of my group are all doing fantastic things, but I haven't had a chance to talk about them today. Tom Barron and Peter McHugh from the University of Oxford, who helped us out with the oligos and the enzyme respectively, and then the funders. And then finally, thank you very much.
Great, thanks Joanne, and very much on time. Thank you for that. And again, it's open for questions from across the panelists and the attendees. So open for questions. You can raise your hand or you can ask the question in the chat. We're getting to that Friday afternoon lull where people's ability to ask questions is probably going down just a little bit. So maybe I could ask a question, Joanne. In the last part of the work, it was quite clear that when you went back to the phosphoric acid, or the that you were back in the game, so to speak, in terms of the activity increasing and the IC50 going down, into the micromolar, whatever, 25, 35 micromolar. Where do you think you need to tweak next? I mean, so where can you lengthen the chain between the phosphoric acid and the uridine, or your ribose type sugar? Is that beneficial or not?
I guess ideally we want to I guess once we have a good idea that something's going to work, here we go. We want to ideally kind of get into structures like this. So we know from other things that we've done, if we have a long oligo chain and we put even a reasonably modest zinc binder on the top of it, that actually, excuse me, we can see pretty decent binding. So the idea now is if we get something that we know is actually pretty good in terms of binding the enzyme, we can put that on top of the oligo. As long as we can get away with essentially the kink we're going to put in the chain, then hopefully we get through to something really quite potent and quite specific as well for our enzyme. So that's where we want to go next.
Okay. Interesting question in the chat from Mark Searcy. Hi Mark, greetings from Dublin. Do general hydroxamic acids inhibit this enzyme, like SAHA for example? And do you envisage using isosteres to get into cellular work?
So we haven't tried a broad panel of other hydroxamic acids. There definitely will be some degree of structure activity relationship. We know that for sure just from trying the two different chain lengths. So the fact that we saw the longer one, which we actually originally thought was going to be better, is significantly worse. So I think we weren't actually able to determine an IC50 with the conditions we tried. So I think certainly if you swamped it with any hydroxamic acid, you would get something, but I think again you'd really struggle with potency issues. And then in terms of going into cells, that is going to be another barrier to overcome with the oligos, because they're not fantastically cell permeable, let's say. But in the first instance, and we can actually do a lot with, if we just lyse the cells open and treat with the probes in the first instance. So I guess we're basically just pushing that problem down the line a little bit.
Very good. And perhaps your most impending biological problem is to get rid of that cough. Well done on giving the presentation. And again, oh, hold on, maybe protides. And thanks for Mark again. Sorry. Maybe protides, thanks for struggling through. There you go. So he's talking about your chat as well, so, or your cough as well. Maybe in the interest of time, we'll stop there, Joanne. Thanks very much again for your presentation. And if you could stop sharing, we will move over now to Stefan Oskarsson, and thanks for taking that place in this. Well done. Okay, so Stefan, over to you. Fingers crossed.
Yeah, let's see if this works now. Can you see that one?
Yes.
And hopefully we'll see.
I don't know if there's a...
Is that okay?
Yeah, perfect. Oh, that's huge, actually.
Yeah,
very
it's huge. So why is it that big?
Yeah, if there's some way of, yeah, maybe 50%. Now, what we can see then is one slide and a bit of the slide underneath. So maybe
I realized that. Normally.
Yeah, 75.
Yeah. So if I do like this, it's just too big, right? Yeah.
That's huge. Yeah, no, it cuts off about 2/3 of the slide.
Yeah. Okay, let's do it like this then, and we'll
maybe
do
bring
it
down. Can you bring that down a little bit, because we're seeing.
That's what I can't do. That's strange. And that's too big.
Yeah.
How about that then?
Yeah, that's again, I only see half the slide there, the top half.
Okay, yeah. I'll just bring this down again.
Yeah.
How about that?
Yeah, I mean, I can see all that slide. I just wonder what it's going to be like for the next few slides. That's the only thing.
Yeah.
How you're going to scroll down through.
I just do it like this, and then I'll do.
Yeah, that's fine. We'll go with that if that's all right.
Yeah, I think that we'll have to go with that. I'm sorry about this.
Okay. Our penultimate speaker, Stefan Oskarsson from University College Dublin. Over to you, Stefan.
Thank you. So we're trying to make fungal vaccines, and I had to scroll also. So the fungi that we're interested in is called Cryptococcus neoformans, and it's like most fungi, it's opportunistic. So it's a very common infections, but normally if you have a normal immune system, you can clear it. But if you have an impaired immune system, it's a major problem. So for example, then for AIDS patients or for patients going through organ transplants. And partly why we are interested in it is it's because it has a capsular polysaccharide, which is a virulence factor. And one problem then in trying to make a vaccine is that it's a heterogeneous one. So it's not a defined structure in the polysaccharide, but it has structural motifs that changes with batches. Still, in spite of this heterogeneity, you can serotype it, and the serotyping is then dependent on the structure of the capsular polysaccharide. And you can serotype it into 4 serotypes, A, B, C, and D. And the ones that we are interested in is serotype A and D, because these are the 2 that infect humans. So here's then a cartoon of the cell wall of Cryptococcus neoformans. So in the outer part, you have the capsular polysaccharide, which is then what we are interested in, which we then call the EuChemS polysaccharide. But then it's also underneath that, it's a very complex cell wall with a lot of other polysaccharides, man and beta glucans and chitins and so on. And we're talking about vaccines, and then vaccines based on the carbohydrates, the capsular polysaccharide. And there's already now a number of really good vaccines based on capsular polysaccharides from bacteria, which are a bit different. They are very homogeneous. They are built up by repeating units which are polymerized, and they are also immunogenic. So you can use just the capsular polysaccharide as a good vaccine. But even a better vaccine you will get if you take the capsular polysaccharide and conjugate it to a protein. So you get a glycoconjugate vaccine, and these are now commercial and brought into vaccination schemes in most countries. For example, in Ireland, and all of these red ones you see here are then glycoconjugate vaccines against bacterial meningitis. And this is just a slide then to show the efficiency of them. So the glycoconjugate vaccine against MenC was introduced in the UK in 1999, where there was a lot of cases. And only a couple of years after the introduction of the vaccine, it has more eradicated the disease caused by this bacteria. And the vaccine is almost a victim of its own success. So the mass vaccination was discontinued in 2016 because it was not needed anymore. So perhaps not a good business idea for a vaccine company to do that kind of good vaccines. So back to the fungi, Cryptococcus, and you can see from these pictures that the amount of polysaccharide is not a problem, but the problem is another one. So if you now try to do a whole cell vaccine, just use the cell, the killed cell, as a vaccine. This time, the capsular polysaccharide, it's not immunogenic, it's an immunosuppressor. So you get no antibody production and no protection. And also then, if you just take the polysaccharide, which works with the bacterial polysaccharides, this time it's not immunogenic. As I said, it's immune suppressors, it's actually disease enhancing. But like with the bacterial glycoconjugate vaccines, you can then activate the immune system by conjugating the polysaccharide to a protein. And thanks to the protein, you now get antibody, you get immune response, you get antibody production, and these antibodies will also then be against the polysaccharide. But what you see here now is a variable efficacy. Sometimes you get protection and sometimes not. And we think that's partly then because of the heterogeneity and the different structures in different batches of the polysaccharide. But from these experiments, these immunization experiments, which are done in mice, we have a number of then interesting biological tools to look more into the development of good vaccines, which is then a library of mice monoclonal antibodies. And these then show either protection or non-protection. So some of these monoclonal antibodies then binds to the cell, to the fungi, and then also kills it. But some of these antibodies just bind and do not then set all these following processes going that will lead to the killing of the fungi, so non-protection. So what is the difference then between the protective and non-protective monoclonal antibodies? Both of them or all of them binds to the polysaccharide, but some starts then the process to kill the cell and others not. Are there different binding specificity? Did they recognize different epitopes, or what is the cause of this difference? And we then thought that it's probably then that they bind to different epitopes. So in this heterogeneous structure, there are then protective epitopes that if these could be used in a vaccine, it would give a protective response and it would be a good vaccine. But we also see then that there are probably other epitopes, and if the antibodies are produced against these epitopes, it will lead to just binding and not a protection. But how to find these epitopes, how to determine the binding specificity of these different antibodies. You can't use the natural polysaccharide because, as I said, it's too structural heterogeneous. So the only way to do that, according to us, is then to synthesize well-defined structures and then screen the different the monoclonal library with these well-defined structures. So what is the structure then of the polysaccharide? Well, more or less it looks like this. So it's a mannan backbone with mannoses 1,3 alpha linked, and then you have xylose substituents either in the 2 or in the 4 position, and glucuronic acid in the 2 position. And depending then on the amount of xylose substitution, you have the different serotypes. So in the ones that we are interested in, the A and D, there's no 4 substitution of xylose. And in the A, there are 2 xyloses on 3 mannoses, and in the D, it's just 1. So that's the heterogeneity we have. And as I said, it doesn't mean that if it's serotype A, it's only serotype A as it seems here. It will also contain the other structures, but in different then ratios and proportion. On top of this, then heterogeneous xylose substitution pattern, there's also a heterogeneous acetylation pattern. So it's known that the acetates sits on the mannose in the backbone in the 6th position, but how they are distributed along the polysaccharide chain is not known. So, well, if we now want to make a lot of oligosaccharide structures corresponding to these GXM structures, they are very, very then suited for block synthesis. So as you say, to do the A and D structure, we would need 2 building blocks, disaccharide building blocks, 1 xylose mannose building block, and 1 glucuronic acid mannose building block. And since we know that the acetylation is important for virulence and for the immune response, we really want to have oligosaccharides that includes the acetates. So what we did was that we synthesized the needed thioglycoside building blocks. And as I said, we're really mainly interested in A and D, so only in the disaccharide building blocks. And we make them as thioglycosides so that we can use them as donor and elongate in this direction. And we have a temporary protecting group here in the 3 position, so we can elongate in that direction. And then we want them with or without the acetate. And that really, really complicates the synthesis. So if we just wanted to make this disaccharide building blocks with the glucuronic acid and the mannose, from 2 monosaccharides, it would take 1 step. But because of the acetates, it then instead requires 10 more steps. So we have to introduce the glucose as a perbenzylated glucose. And then we have to change this into the benzylated glucuronic acid and introduce the acetate. And as I said, that's 10 more extra steps just to get to this disaccharide building block. Anyway, we have managed to synthesize these building blocks, right? And then we, of course, started to put them together. And problems in making the building blocks, but joining them has worked very well throughout. So we started with using these conditions. It's a thiophilic promoter, it's diethyl ether, and we choose this combination because we know that's normally good for alpha selectivity. And as you heard in Owen's talk, making beta mannosides is difficult. Fortunately, making alpha mannosides are not that difficult. So this was the first one we tried, and we never tried anything else. That combination has worked all through from day 1 to probably day 5,000 now in the project because it's a long project. So acceptor then with a spacer, so we can do the conjugation to protein later on, introducing of the first building block, removal of the temporary protecting group, introduction of the next building block, C, high yielding, introduction of a third building block. And here we stopped for a while because we thought that we had an interesting heptasaccharide containing the type A triade. So we deprotected that, and you see only benzyl protecting groups, so just one deprotection step, removal of the benzyls, catalytic hydrolysis, and also we reduced the acid, so we have a handle here. And we use that handle then to make biotin conjugates, and these are then to put on streptavidin ELISA plates for screening of antibodies. And we also did the protein conjugate for immunization experiments. And as I mentioned, we have the possibility then to put different acetylation pattern on. We made one with 2 acetates, one with no acetate, one acetate and one with no acetate. And we have worked with this for a long, long time, making smaller structures up to a pentasaccharide. But now with the heptasaccharide, it was the first time we found structures that was recognized by the monoclonal antibodies. So we found 7 monoclonal antibodies that bound to this heptasaccharide, and these are the 3 different acetylation patterns. And as you can see, the monoclones doesn't really care about the acetylation pattern. So that was good results. And also when we did the immunization, we got good antibody titers. We could show that the antibodies bound to the polysaccharide and to the fungi. But when we did the challenge experiments, the mice died. And when we looked at monoclonal antibodies that had recognized this heptasaccharide, we saw that they were all non-protective antibodies. So we kind of thought that we had proven the second part of our hypothesis, that there were non-protective epitopes like this heptasaccharide, where when you introduce them into the vaccine, it will give antibody response, but non-protective antibody response. So of course, this is the one we're looking for. And we were a bit confused then, because if you look at the antigen binding part of the antibody, it can accommodate not more than a tri-tetrasaccharide. And since we have done all the iteration, all the possible structures found in the GXM polysaccharide up to this heptasaccharide, why haven't we found a structure that was recognized by also the protective monoclonal antibodies? So the solution to this, a rather perhaps obvious one, is that probably what we would need is larger structures where we form secondary structures that will give conformational epitopes. So not a linear epitope that is recognized by the protective antibodies. So to look at that, we started a collaboration with Michelle Cuttle from Cape Town, who is an expert in modeling polysaccharide structures. And she found that, not unexpectedly, that the smaller structures are very flexible. But when it started to come up to octa-decasaccharides, she could see that secondary structure was being formed. And here we can see, so when there are larger structure, the backbone, the mannose backbone, starting forming a helical structure. And then, for example, then in the type D, the glucuronic acid and the xylosubstituent is put on outside this helical structure. And this is then the A serotype with 2 xylos, and here are the acetates in there. And you can really imagine that it's these kind of structures that the immune system would see and make antibodies against. So that required larger structures and more synthesis. And we still very much believe then in the building block approach, but we were targeting now up to trimers of these, so octadecasaccharides. So to do that using disaccharide building blocks would require 9 glycosylations. So it would really be a help to have larger building blocks like a tetrasaccharide building block and a hexasaccharide building block for the serotype A. So using the disaccharide building block again, one of them we turned into an acceptor, the other one we turned into an orthogonal donor, a trichloroacetamidate that we can activate without activating the thioglycoside. Initially, we tried these conditions and we got a 30% yield. So we got it, but not a good yield. So as always, you try to optimize, you change the promoter, you change the solvent, but we could never get above 50% yield. But then just to highlight that it's not only changing the conditions, but also in this case, the order of adding the reagents. So normally when you do a glycosylation, you mix the donor and the acceptor, add the promoter. In this case, if you mix the promoter and the acceptor and then add the donor dropwise, we doubled the yield. So now we had almost quantitative yield of the tetrasaccharide, which we then can turn into an acceptor. And of course, we thought now that we know exactly the conditions and the way to do the hexasaccharide. But although it's such a similar building block, now the yield went down to about 45% again. But if we change this temporary protecting group from a NAP group to chloroacetate, we were up to good yields again. So now we had the building blocks that we wanted and we could start putting them together. And as I said, once we have the building block, putting them together really works well using exactly the same conditions as the first coupling. So in all the cases, this is the glycosylation yields, right? And you see that they are really good. And that was both in the serotype A and the serotype D. So these are after the glycosylations, right? So then we have the target, the protected target structure. And then, as you quite often say, it's just deprotection. And the first time we did the deprotection on the heptide was not a problem. But now, when we did the catalytic hydrolysis, we had major problem because initially we didn't know what it was. We had some side products. We had signals in the NMR around 1-2 ppm. And initially, then we found out that it was that we also had some reductions of the phenyl and the nephyl groups. So producing cyclohexyl groups then that of course was not able to be removed. So we looked a bit into that and we found that there's a big difference in the quality of commercial catalysts. And we actually made a rather thorough investigation of that. And through this, we found a good commercial catalyst that solved this problem so that we could get the hydrolysis without getting the reduction of the aromatic system. So now we had this library of 27 different GXM structures ranging in size then from a disaccharide up to a octadecasaccharide. And what we also had now was that we had an array printer, so we didn't have to use ELISA to screen the monoclonal library, but we could print the GXM structures onto a microarray, which meant that we didn't have to do chemistry, didn't have to make the biotin conjugates, and also that we could use much less amount. So on the microarray, we print micrograms instead of then in the ELISA, we often have to use milligrams. So 5 milligrams of the product is good enough for almost 1,000 arrays, so it will last forever. So that's really good. So we print them, and then we can screen the array with the monoclonal antibody library. What we've just started is also screening it with human sera from AIDS patients having or having not a Cryptococcus infection. It's a new collaboration with a group in New York. And of course, what we want is a vaccine that works in humans. And unfortunately, most of the work that we're now doing with a mouse will not be valid when going into humans. But still, we have to do it. And if we found any hit, and what we mean with a hit is then a structure that is recognized by a protective antibody, we will use that in forming a conjugate vaccine and looking how that will behave when vaccinating mice. So we have this larger library then of GXM structures, but what we did initially was when we had 10 structures, we printed those. So we had a smaller library up to a decasaccharide, and we screened that with 3 antibodies, 1 protective and 2 non-protective. And we were very, very then excited by finding that it was one of the structures was recognized by a protective antibody, and that was the decasaccharide, the largest one, kind of proving that it's probably a conformational epitope that is recognized by this bacteria. So when we got that information, we immediately then conjugated the DECA to a protein, and we are now performing immunized studies, or rather, these are performed at Johns Hopkins University, and we're just waiting for the results to see if this will give protection or not. We also then printed a larger array with all the structures that we made, and also looked at many more monoclonal antibodies, screening the array, both protective and non-protective antibodies. And what we found then was that acetates more or less are needed for the recognition. So you have 4 antibodies, and they all recognize the DECA, but only this one recognizes also the non-acetylated one. All the other ones require the acetates to bind to the structure. And then we continued, and then we got a bit confused again. So with this array now, we can get a really good knowledge about which structure that they recognize. And we see that it's really larger structures that is being recognized. So we need the confirmation of the secondary structures for recognition. But if we look at it, here we have the A structures, here with D structures, only the larger structures is recognized. Nothing strange there, but these are 2 protective antibodies. But if we then continued, we saw that all of them had very similar recognition and binding pattern, independent on if they were protective or non-protective. So I think we're starting to think that we have got this wrong. There are no protective epitopes. There's something else. Both the protective and non-protective antibodies recognizes very similar epitopes, and the difference, if they are protective or non-protective, must be in the finer details of this binding. So that's what we're trying to do now, look more in detail on this binding, both using then trying to crystallize the complex between them, but also using NMR and STD NMR to look at the finer details of the binding. So just to finish off quickly, what we also found with these monoclonal antibodies, completely then different from their vaccine effect or immunogenic effect was that they could also function as enzymes. So they had hydrolytic activity and they could cleave the polysaccharide. And we thought that now with these oligosaccharides, we had really good tools then to investigate this hydrolytic activity in more detail using then FRET probes. So if you have then a chain, and these are very much used then with nucleic acids and proteins, and you put a fluorescent group and close by a quencher, you have no fluorescence, and then when you have hydrolytic activity cleaving then the peptide chains or the nucleic acid chain or the oligosaccharide, these are then moving away from each other and you get the fluorescence. So what we did was that we then produced the decasaccharide again with two amino groups, one protected and one non-protected. And using that one, we could then introduce the quencher and the fluorescent group to get a FRET probe. And this is then really good. We could then very quickly then determine if an antibody had this catalytic activity, because then we would see fluorescence, and we could also do kinetic on it. So you can see here that many of the antibodies have this catalytic activity, but they have very different amount of catalytic activity. And we can also investigate what substrate is better for the activity. So here you see that the acetylated decasaccharide is a much better substrate for this catalytic activity than the non-acetylated. So that's the end of that. I think we come a long way, and it's a nice combination then with the expertise of the biological collaborators and our expertise in making these oligosaccharide chemical biology tools. So I'd like to thank all the people involved in this, and the blue ones here are the biological collaborators. So it started out with Professor Cherniak at Georgia State University, and now we continue the collaboration with Arturo at Johns Hopkins and Lisa Ann at Albert Einstein College of Medicine in New York. And here are all the people that have worked on it. The ones in black are the ones working on the project when I was in Stockholm, and the ones in red and green are the ones that worked with me at UCD. So I thank them a lot. Thank SFI for the funding, and I thank you for your attention.
Great, Stefan, thank you very much. And it is indeed, and has been a great story, and shows the power of synthetic chemistry to be able to make those very large decamers, etc., of carbohydrates, but in a pure form. So then you can go and test them. So again, it's open for questions from panelists and attendees. So please raise your hand to ask a question or put your question into the chat box. Owen McGarrigle, off you go, ask your question.
Stefan, beautiful chemistry. Were you tempted at all to try acetylating the already synthesized oligosaccharides with the hope that the acetylation pattern you might see would be what nature would produce anyway? Or is the acetylation produced on oligosaccharides in nature? Do you know?
Yeah, so initially we tried that, but I think that the real good thing with the block synthesis is that you can determine where you want to put the acetates. So the problem is, of course, then that we don't really know where they are in nature. And I didn't talk about that, but if you saw when we did the larger structures, we only choose one acetylation pattern. And why we only choose one acetylation pattern is because it would have been too complicated to have more than one. and also that we have some indications from Robert Cherniak, who did all the structural analysis, that this is actually the acetylation pattern in the native polysaccharide. And that is probably not as heterogeneous as was thought before. But because of the other heterogeneity, you can't do really good structural analysis. So you have to guess still, but that's our guess that this is the correct one. What we thought about was trying to get the enzyme putting the acetates on. So use the non-acetylated synthetic oligosaccharide as substrates for that enzyme. But there's been investigation showing that the acetylation is not the last step, but it's a step that precedes the introduction of the substituent. So you have the mannan backbone, you put the acetate on, and that is the substrates for the transferases putting on the xylo substituent. So it wouldn't work. The enzyme will not accept our oligosaccharides as substrates.
Okay, thank you. That makes
Thanks,
sense.
Owen, for that, and thanks, Stefan. And maybe in the interest of time, I don't see any further questions coming through. We'll stop at that stage. Again, super presentation. If you could unshare your screen.
Yep.
Now we move on to the final talk of the day for Professor Donal O'Shea at the Royal College of Surgeons in Ireland, University of Medicine and Health Sciences. So it's a bit like the flights at the end of the day. Donal, sorry, you're a bit delayed. It's just accumulation of things. Good, I can see your slide. And if you go to full slide, hopefully we won't have any further problems with technology.
How's that?
Perfect. Yeah, great.
Fantastic. Thanks, everybody, for hanging in there till the end of the day on a Friday. I'm just going to get my pointer up. The title of my talk is quite unusual, I'm sure, for a meeting like this. It's called Forecasting Vaping Health Risks Through Neural Network Model Prediction of Flavor Pyrolysis Reactions. So it may not sound like organic chemistry, but I am an organic chemist by training. A lot of our other research is into chemical biology and synthetic chemistry, but this is sort of a pet project that has been working on for the past couple of years. It's in collaboration, I should stress, with a fantastic postdoc in my team, Dr. Dan Wu, and a very close collaboration with IBM Research in Japan. And you'll see pretty much halfway through the talk why that is, and that's with Dr. Akira Kishimoto. It's very much a project that sort of comes about just from knowledge of organic chemistry rather than really any new, very complex chemistry. And it comes from the very beginning of organic chemistry, and that's pyrolysis reactions. But the story actually really revolves around a public health issue, and that is to do with vaping. And I'm going to give you a very, very brief background to vaping if you're not familiar with it. It really is quite a new event, I guess, in humankind. Vaping was first patented only back in 2003 in China, but very rapidly it became onto the commercial markets in Europe and in the USA by 2006. And soon after that, in 2008, 2011, the public health authorities in England and in New Zealand began to recognize that perhaps vaping was a way to have a less harmful smoking, essentially, and try to maybe perhaps be an aid for heavy smokers to stop smoking and to transition into vaping, and ultimately to not having any nicotine addiction whatsoever. But as time went along, by 2014, the commercial value of these was becoming very well recognized. And by 2014, there's over 466 vaping brands worldwide and 7,764 unique flavors. And this type of combination of marketing and flavors began to sort of shift the demographic of users very much to younger users. And this was sort of highlighted in 2016 when the CDC in the United States warned that both marijuana and tobacco vaping were being widely used in US schools. And there's been subsequently many reports of that since. In 2017, the first sort of health issues began to really begin to emerge due to vaping, and that was the first clinical case of an acute respiratory failure after inhalation of vaporized cannabis oil. But it really was in 2019 when this became into the public domain very widely, because there was a severe outbreak of lung injuries associated with vaping occurring in the US. And really there was a lot of confusion as to why these were happening. Within about a year, there had been 2,758 recorded cases of these types of lung injuries with 64 deaths. And just then to put it in context, in the EU and in an Irish context about vaping, there was an EU-wide survey published in 2021 that revealed that Ireland has the highest vaping product use of 7% of the population in this survey, saying that they have tried vaping products. And that's compared to the EU average, which is only 4%. But this is continually growing, especially in a younger demographic. So when you're talking about vaping, and because my particular presentation would touch on both, you have to realize there are actually two categories of vaping. One is vaping of cannabis or THC e-liquids, and that is where essentially you're vaping cannabis oil. And this obviously illegal in Europe, but you have to recognize that this is legal in many states in the US. And in these e-liquid solutions that are used, which essentially are your reaction solution, as you'll see in a moment, they needed a dilutant or a solvent. And what they used was this compound here, vitamin E acetate. And vitamin E acetate is very widely used in cosmetics and in foodstuffs and other applications, because it is inexpensive and a lipid. It's used as its acetate rather than the natural product vitamin E, because in products, vitamin E doesn't have the same shelf stability as the acetate, so hence it's used as the acetate. So the story here is that essentially it's widely available and it's cheap. In comparison, in nicotine e-liquids, which people may be more familiar with, the drug that essentially is being delivered is nicotine or the nicotine salt, and the carrier or the solution in the e-liquid is propylene glycol and vegetable glycerin and water. But what has emerged, most certainly in the past decade, is that a huge number of flavors are being used in these to help commercialize the products. And currently, there's over 180 chemical flavors in use in Europe today in these products. And I'll come to this in the second part of my talk. Also, again, in case you're not familiar with vaping, the devices themselves vary dramatically from one brand to another, but they can be sort of categorized into two types. Those that are pre-filled cartridges, and they have essentially no power settings available to be adjusted by the user. These ones are less popular. The ones that are most popular are where the user can fill a tank, which is situated here, with whatever e-liquid or solution they wish, and they have control of the power settings so that essentially you can go to higher or low temperatures. So how does, if you think about this is just a means of delivering something to the lung, how does it vary from, say, delivering of a drug such as salbutamol to the lungs, which is obviously very, very widely prescribed and used worldwide for asthmatics? Well, the big difference between a salbutamol inhaler and a vaping device is simple in that one is heating, and that's the vaping device, and the other is not. It's using a pressurized canister to deliver this particular drug to the lungs. So obviously talking to this type of audience, which often I'm talking to a non-chemistry audience on these types of topics, what happens when you heat a chemical and what can happen, and what you look at, the mode of heating of these particular solutions is very, very archaic. It's akin to something like a 2-bar heater where you're passing electrical current through a wire, and these are sort of images taken of these types of devices. The temperatures that you can reach are from 110 to 1,000 degrees Celsius. Really very high temperatures can be reached. So obviously we would all recognize that if you're heating chemicals into these type of temperature ranges, you really do risk going through a thermal activation energy, and whatever reagents or reactants, as we would call them, that are in your solution or your e-liquid have very high likelihood that they're going to start doing chemical transformations to make new products. And really, remarkably, this has not been properly understood in a public health arena. So our contribution into an understanding of what happened in the United States in 2019 centers around our work that started in August of that year, when we became interested in reports that were essentially in the proper press, being highlighted by the CDC, that they were recognizing that there were an increasing number of very young, usually teenagers or young 20-year-olds arriving into hospitals with very unexplainable acute lung injuries. And what was in common among all of them was essentially that they had been vaping cannabis oils. This shows a demographic of, or a plot of essentially the progression of this particular outbreak of lung injuries, and you'll see it petered out around February 2020. And overall, 68 people have been confirmed dying from this particular disease with numerous hospitalizations. What was common, what one recognized in the summer months over the 2019 was that this particular agent, along with THC or cannabis oils, was in these particular vaping solutions, and this is vitamin E acetate, to what I showed you a moment ago. This, as I said, got very much attention in the popular press and in the scientific press. So this is an issue, article from an issue of Nature in October of that year, where they're talking about scientists chasing the cause of this mysterious vaping illness. And there was some confusion and different theories being proposed by different medical scientists in the United States at the time, none of them that would really fit the types of injuries that were appearing in patients. So as I said, around August of that year, we decided we would do a little bit of chemistry detective work to see could we essentially illustrate a chemical basis for why these late vaping lung injuries were occurring. What was known was that vitamin E acetate had been found in the lungs of these patients, and the majority of patients had been vaping THC-containing mixtures. So our theory was essentially that there was a terminal decomposition in the vaping devices, or a pyrolysis of them, of the vitamin E acetate, and it could produce a very toxic gas called ketene. So when you look at the chemical structure of vitamin E acetate, it was in fact a very small acetate group that caught our attention first. And we speculated to ourselves that the pyrolysis of this compound could produce ketene gas, a very small molecule. Ketene, if you're not familiar with it, has a boiling point of minus 56 degrees Celsius. You can't usually buy it because when it's used, it's prepared and used in situ, but it is used industrially in as an acetylating agent in chemical synthesis and used for the manufacture of acetate esters. What's not really well recognized, because there has been no real major outbreaks of accidents industrially with ketene, is what is its actual toxicity, but there are some early reports that did studies on it back in the 1930s, and they showed that it was very highly irritant gas to the respiratory tract, and its toxicity and mechanism of action is similar to phosgene. So really a highly toxic gas. So when we wanted to quickly investigate this, what we looked at was some of the early literature in the pyrolysis of aryl acetates, and this work going back to 1938 in some of the classical original pyrolysis chemistry done by Hurd. He showed that the pyrolysis of phenylacetate at 625 degrees gave a really good conversion to ketene and the corresponding phenol. So we wanted to investigate could vitamin E acetate do this similar type of chemistry in this region, essentially of the acetate group forming ketene and vitamin E and perhaps other products too. So to do this first, before we took it into a vaping device, we wanted to investigate it by using mass spectrometry, because we believe that the mass spectrometry would give us an indication of what bonds would be most likely to break and what the fragmentation patterns of the mass spec could match the pyrolysis chemistry. So if we look at phenylacetate as sort of a test molecule, we could see that the predominant fragmentation in the mass spec was loss of ketene, again indicating that matched what was in the literature. When we looked at vitamin E acetate, we could see again the fragmentation patterns, both of them indicating the loss of ketene, so perhaps showing that we were on the right track. And as a control, we could see vitamin E itself did not produce this mass spec fragmentation pattern. Obviously, we had to go into then some experimental work. So what we did was we actually took vitamin E acetate and we vaped it in simple commercial, readily available vaping devices. The proton NMR of the isolated material here is on the bottom, but on top is the pristine vitamin E acetate. And you can see there's been huge degradation of the molecule just by passing it once through a vaping device. And we could separate out many of these components into volatile and non-volatile components and identify quite a large number of them. There was a large number of different alkenes, benzenes, dienes, and organic oxidants such as duroquinone, but at least over 25 different products have been identified, and in some other subsequent work done by other groups, even more have been identified. So you can see there's an extensive terminal decomposition, but what we couldn't see was a key agent we wanted to see, which was ketene, because it's too reactive to isolate. So to actually prove that ketene was being formed, we had to set up a trapping experiment where essentially the pyrolysis material coming straight out of the vaping apparatus from vitamin E acetate was bubbled into a solution containing benzylamine, so we could essentially acetylate it and form the corresponding amide and detect that amide in the crude mixture, essentially from the vape. So we published this paper in early 2020 in PNAS, and it was really quite nice to see that even before we published a paper from our preprint, it was being cited by the CDC in their paper in the New England Journal of Medicine on December 20th, 2019, talking about this new compound that they'd never heard of before, which was ketene, and how it could be split off from vitamin E acetate. And over the past couple of years, there's been several reports that have confirmed this pyrolysis chemistry. And only very recently, in a preprint appeared a few weeks ago showing another group had confirmed our trapping mechanism with a similar compound. So that was really quite gratifying so that we could contribute in that way into something in a public health manner. And soon, as you might have seen from that timeline, around 2020, early spring, March, something else happened, and we weren't really having easy access to our laboratory, shall we say, without having to mention the COVID word, I suppose. And what we wanted to think about was, well, what other types of ways could we investigate this and see, did it have any relevance to nicotine vaping? If you think about what is nicotine vaping, essentially when it first started out in its first iteration, there was only 4 compounds in an e-liquid solution for nicotine vaping. That was nicotine, propylene glycol, vegetable glycerin, and water. Now, these 2 compounds in themselves have issues, as does nicotine for other reasons as well. But what has subsequently happened in the past decade or so is that a huge number of chemical flavors are being used. And in many cases, the chemical flavor is the predominant component within the e-liquid. And the consequence of using these chemical flavors has really not been investigated to any great extent whatsoever. So to give you a sense, because I know I wasn't familiar with these beforehand, this is a snapshot of 100 of these chemical flavors, and not to linger on them, but even casting your eye across them, you will see every type of functional group, aromatic rings, heterocycles, just about everything an organic chemist would look for. Very complicated structures, all relatively low molecular weight. And here's another 100 of them. All of these currently used. They've all come from the food industry, where they're used as additives in food. So they have a good safety profile if you're eating them as components or flavorings in sweets or foods. But they have never been tested for heating them to high temperature and inhalation into the lungs directly afterwards. So if you think about tobacco smoking and the history of trying to show that tobacco smoking is not good for your health and causes cancer, tobacco smoke contains 70 known carcinogens, but it takes decades of accumulative damage to cause disease. And this can be very difficult to try to prove in advance that there's going to be a problem. So what we wanted to do was to develop a new holistic approach to try to capture the risks associated with vaping based upon the chemical pyrolysis of these particular flavors, so that essentially you can see what compounds are being produced. We could recognize their toxicity effects, and maybe then from that understand what diseases may emerge in about 10 years' time for people who are long-term vapers. Also, I guess recognizing that if there's 180 to 200 different flavors currently in the market, if we go and try to do that experimentally, even if we have access to our laboratory as normal, we will have a long time to try to make any progress. So we really had to come up with a complete different approach on how to do that. And what we turned to then essentially was to use artificial intelligence to try to use that to predict the chemistry, and from there to build risk profiles. So this is the nearest I have to a reaction scheme, so very different from our normal chemistry. And there's no reactions taking place. Essentially, it's all done in a computer. And what we've developed is a process to do e-liquid risk profiling based upon the flavors that are in them. And the way we did that, we chose 180 recognized and confirmed flavors that are used in all across the EU in e-liquids. And we convert those flavor structures into their corresponding smiles. And the smiles is simply a way that the computer can understand the chemical structure. And then from those 180 flavors, we use a neural network form of artificial intelligence to predict 25 pyrolysis reactions for each one of those flavors. Because we suspected, and we are an experimental group, that just using artificial intelligence alone may not be sufficient to convince people, we wanted to have some experimental input into that as well. So what we have looked at is the EIMS, that's the mass spec, electrical impact, mass spec data that is available for these 180 flavors from an online database in the NIST, and the NIST is the National Institute of Standards and Technology. And that allows us see the mass spectral profile of these particular flavors and all the fragmentation patterns of them and the fragments that are produced. So essentially, we combined the artificial intelligence pyrolysis products with the fragmentation patterns from experimental work done by the NIST and available online. And we correlated the neural network predicted products and the EIMS data, looking for molecular weight matches essentially between the two. And that's done in an automated fashion by software. We identified the molecular weight matches, and then we screened those molecular weight matches against the GHS, and GHS is the globally harmonized system for chemical hazard classifications. So that's just the system that's used to classify all the chemicals in our laboratory and their hazards. And we were matching the smiles of these predicted products, screening them into PubChem in an automated fashion and retrieving their GHS data so we could classify how toxic they were. We've also, and I'll briefly touch on this and I won't dwell on it too much, but also recognizing as organic chemists that we want to know what the activation energies of these are. And we wanted to do this also using artificial intelligence rather than DFT calculations. So we can predict the activation energies for the most, I guess, worrisome reactions. And all of that then is compiled into a flavor risk report for each one of them. So that essentially you can screen it and see what is predicted to be produced and what is the toxicity of them. So very briefly to try to go through each stage of this. First of all, to select an AI prediction of chemical transformations. We didn't develop any new AI for this. We were looking at what was available in the literature, and you're probably familiar with some of the ones that have been reported recently. The IBM have their own reaction predictor, and there has been a variety of different neural network systems. The one that we actually focused on, as you'll see in a moment, is the Weisfielder-Lehmann neural network system to do our particular study. But all of these particular models of AI prediction for organic chemistry is in and around synthetic transformations, where you have a reagent A and a reagent B under a set of conditions to form products C and D. What we're looking for is something a little bit different. So we had to modify or sort of expand a little bit the one that we used, in that we really have a different type of reaction where we have one reagent, which would be our flavor. The conditions are essentially just thermal decomposition, but we will end up making an array of different products because pyrolysis chemistry is like that. It's quite messy, and you usually make a whole range of compounds, as I showed you in the vitamin E acetate example. What's important to recognize is that all these particular products also will have lower molecular weight than the starting material, and that way we can also essentially correlate those against their fragmentation patterns, and that's what I alluded to a moment ago. So the neural network the AI that we chose to use is one that was published by Coley et al. In 2019 in EuChemS. It's using the Weisfielder-Lehmann neural network, which has been around for quite some time, but he very nicely developed that for predicting chemical transformations. I'll just call it the WL neural network for now on for simplicity, but the WL neural network is what's termed a graph convolution network, and it functions by prediction of the reaction centers based on bond changes for every pair of atoms in the molecule. So it is looking at every atom in the molecule and every bond in it, and it's making its predictions based on that. Why we chose this particular one was because we could adapt it to allow for the predictions of numerous potential products, and that those products could be ranked in their likelihood to be produced. And that's a nice unique feature of this particular neural network. So I'm not going to labor on this too much on a Friday afternoon, but when you're doing these types of systems, first of all, you need to train your neural network. The data that we use to train the neural network came from the patent literature in the US Patent Office, and this was a database that had been built up by several groups over the past number of years, and we used 354,937 chemical transformations, and that's how the network learns about chemistry. Then we would essentially use our molecular smiles of the 180 flavors, and essentially the network then will go through a series of iterative learning exercises where essentially it's learning everything it can about each molecule in terms of what atoms are in it, what bonds are in it, what are the local atom features, what are the global atom features, and so on of it. Once it's done that, it was going to a sequence of predicting pyrolysis reactions. And it predicts, we set it up on purpose ourselves, we chose it to predict 25 predicted pyrolysis transformations for each flavor, knowing that there would be a spectrum of products that could potentially be made. And then it enumerated them based on the most probable bond changes. Because it does that enumeration, it's then able to do a neural network prediction and rank the likelihood of these products being formed from 1 to 25 based on probability. So the outcome of this essentially is that the neural network predicts 4,500 pyrolysis reactions for us in one go. That's 25 reactions for 180 flavors. And that the outcome of that was that it generated, in fact, 7,307 products from those reactions. We then wanted to identify from those 7,307 particular predicted reactions, products, excuse me, which ones were the most likely. So we cross-correlated that against the mass spec data for each one of those flavors. So this is just giving you a representative mass spec, which looks like any other mass spec data taken from the NIST, which is available online. And essentially, we're looking at the mass spec fragmentation pattern, their molecular weights, and matching it to the molecular weights that are being predicted for the products from the neural network. We set a 5% threshold of peak abundance for the data to be used so that we weren't just reading noise or isotope patterns within the mass spec data. So the molecular weights of 7,307 neural network predicted pyrolysis products were cross-correlated against EuChemS spectral data, all done this by software, luckily enough, none of it by hand. And that identified 1,166 mass matches between the neural network predicted pyrolysis products and the EuChemS fragmentation data for those particular flavors. So we focused just on, sorry, I'll just go back on this 1,166 because they essentially were being predicted, if I put that in inverted commas, by two methods, an experimental one and by the neural network. So just looking at those ones, we then turn to PubChem, and if you're not familiar with PubChem, and I'm sure everybody is, it's the world's largest collection of freely accessible online chemical information. So what we wrote some software so we could do an automated identification of the classification hazards using the GHS system for simplicity for all 1,166 neural network EuChemS predicted pyrolysis products. And the PubChem hazard data then gave us matches for 1,071 of those particular compounds. We looked at them, just broadly put them into categories of compounds that have acute toxicity, health hazard, or an irritant that have none of these particular three hazards or were not in the database. And the results that came back were quite startling in that it was predicting that there was 127 acute toxic compounds potentially that are being produced from these flavors, 153 health hazard compounds, 225 irritant compounds, 566 compounds were not predicting for any of these three hazards, and only 95 compounds were not in the database, showing that, again, the neural network is really predicting real possible compounds, not just random compounds. What does the sort of collection of this work looks like in terms of a risk report for each one of these flavors? This is just an example of what it looks like for this particular flavor, alpha-methylbenzyl acetate. So what we would have is a 25 ranked neural network predictions, which ones are matched from a mass spec fragmentation pattern, and which one and what their GHS corresponding hazard is. So that way we can link the chemical transformation of pyrolysis with the products, with the hazards that are associated with them. So from that way, you can envisage where the diseases are going to emerge in the future. So for example, this one is number one ranked prediction is that this compound will produce styrene, which you would probably think it was not the greatest thing to be inhaling on a regular basis, and many others, and benzene and so on. Just to show that it isn't just predicting the compounds that, and I'm not going to go to this one in detail, but really what's really exciting is that you can also now, from a report that came out very recently from a group also in MIT, this Professor Green's group, published in 2020 and a subsequent paper in 2021, you can use a very similar neural network system to predict activation energies for reactions. So essentially, ethyl acetate is the example I've just happened to chosen here to show a representative one. It's a very commonly used flavor in the e-liquids, remarkably enough, and it's well recognized that one of the decomposition pathways through pyrolysis of ethyl acid is an elimination of the alkene and acetic acid, so you get ethene and acetic acid. So we wanted to be able to predict the activation energies, not just of one reaction, but of thousands of reactions. So to do that, you have to go through a process of automated reaction mapping, which I'm not going to labor on. You have to train them, and there is only one training data set available for that, which comes from quantum chemistry calculations from this level of theory, which was essentially published in 2021 only by Professor Green and his team from MIT. So we've essentially used this particular neural network system and this training set to predict the activation energies for 610 of the more relevant reactions that we were identifying from our previous results that I've just shown you. What we see is that we were predicting activation energy values for anywhere from 39 to 120 kilocalories per mole. So it gives a very wide spectrum of activation energy predictions. What I can say at this stage with this particular prediction, it's not going to match your DFT calculation, but it most certainly gives meaningful results. So for example, if we look at the activation predictions for 10 acetate esters, which are fruit flavors commonly used in e-liquids, for an acetate ester that has a beta hydrogen in this general structure here that has a beta hydrogen in this position, you would anticipate from the literature that there are 3 particular decomposition pathways. One is the one I alluded to in the previous slide for ethyl acetate, is that you would have elimination of the corresponding alkene and acetic acid. Another one is that you would have elimination of ketene with the formation of a corresponding alcohol. And the other one would be the breaking here of this carbon-oxygen bond to liberate out 2 carbonyls. We could very readily predict the activation energies for each one of these particular different scenarios. And you can see here, and I'm not going to labor on it, a whole variety of different acetate esters, some of them containing some complicated functionality rather than just simple ones like ethyl acetate. And we could look at the activation energies predicted for each one of those pathways. And what was very sort of reassuring is that the lowest activation energy pathway was pathway B, which is sort of consistent with what you would expect based on DFT reports in the literature. So it was matching the broad trend, what you would see in the literature. So what that's saying is that these types of compounds, such as the acetate esters with this beta hydrogen available for to affect the terminal elimination, is most likely to be producing alkenes of this type. Not to say that the others won't be produced to a lesser extent, but it allows us to identify the most probable pathway, I guess. And I think this is something that will dramatically improve going forward into the future as the database get better. And then finally, just to show that it isn't just about prediction, we can then ultimately try to match this back to other experimental work being done by other groups. And these are just 2 reports where what has been looked experimentally from a flavors point of view is that it has been shown that a variety of volatile carbonyls are produced by pyrolysis of different flavors, but because the flavors are always used as very large mixtures of different compounds, it's not been possible to identify which flavor is producing these particular volatile carbonyls. So the types of compounds that can be detected experimentally fairly readily are formaldehyde, acetaldehyde, propionaldehyde, and butyraldehyde. But what we can do is say, for example, here we just screen our database now and say which compounds are predicting to produce acetaldehyde. And then we'll get a list of structures and say, these are the ones that are most likely to produce acetaldehyde. And then also we can see if these compounds are producing acetaldehyde, we can obviously chemically recognize where it's going to be coming from, but we also see what also is being produced that has not been detected in these experimental tests, because these are only a small part of what are more complicated structures. Okay, I'm almost finished there. So just to complete what I wanted to say is that it's important, I guess, in this area that often gets a lot of attention in terms of public health, is that we recognize the limitations of the study and where we are at this stage with this particular study, and identify areas that warrant further development. First of all, what we should say is that only the first phase of pyrolysis products have been explored. So from a chemistry point of view, we have limited ourselves to just the first phase of pyrolysis products, but we know in that once you produce the first pyrolysis products, it may undergo a subsequent pyrolysis products, and we haven't yet built that into the neural network prediction, but we believe it can be. Also, there can be cross reactions between different pyrolysis products to make different compounds yet again, and we haven't built that into the network yet, but we believe it can be. We have not yet started looking at combustion products, and that's combustion products of the flavors themselves and of the pyrolysis products. But we believe that can be done also in the neural network predictions by including oxygen as a reagent. A significant limitation for all, I think, prediction of organic chemistry transformations is the training sets. And as training sets get bigger and better, the neural network predictions and the AI predictions can only improve. But this is something that will probably require the work of numerous groups around the world to make the best training sets for these types of predictions. And also what we're looking for is ways to improve the neural network ranking of the reaction predictions. So we are predicting 25 pyrolysis products. We see some of the higher ranking ones are really, there is a bias towards the higher rankings being correct, but we still see that there is room for improvement there in being able to identify the most likely products to be produced. So to conclude, on a Friday afternoon, what we're really trying to attempt here is something quite different in terms of organic chemistry. We're trying to use chemistry-related AI, recognizing that it's going to continually advance over the coming years, probably at quite a high speed. And what we believe it offers a means to reveal the longer term health risks of vaping in advance of the clinical disease emerging in the general population. So rather than waiting for patients to arriving in a hospital with conditions, perhaps if we can use AI with our knowledge of organic chemistry, we can actually predict what diseases are going to be emerging maybe 10 years from now, and maybe for once prevent them. Just to finish, I've got to acknowledge that, again, like I said in the first slide, it's very important to recognize that this is collaboration over the past couple of years between myself, Dan Wu, a postdoc in my group, and Akira Kishimoto, who's a researcher, an IBM researcher in Japan. It is sort of a side project within my group. This particular one is not the main efforts of my research team, but I want to recognize Cathal, Niamh, Sheila, Jacqueline, who do lots of work in terms of chemical biology, synthesis, and fluorescent imaging, recognizing the people who fund my group over the years. And thank you very much for your attention this afternoon, and I'm happy to take any questions if there are any.
Great, Donald, thank you very much. Superb talk to finish up the day, and really what a combination of chemical intuition and the importance of understanding basic chemistry, how important that is, but also really brilliant application of artificial intelligence to help you solve the problem. And it really is a problem. That's the worrying thing coming out from your talk. My first question, if you don't mind me asking a question, is there any regulation in this area at all?
No, almost none.
That's quite worrying, isn't it? When you look at the usage of e-vaping, and when you think about drugs, the FDA is such such a highly regulated field. But who's dropped the ball and not keeping their eye on this?
I guess it's not that it's dropped the ball; it is actually the approach that's taken for new technologies. It sort of falls into that remit. Quite often it's put out there into the public to see what happens, and it's up to scientists then to try to say there's a problem. It's the complete reverse of what you would think, but this is not uncommon. So only now in the US they're beginning to seriously consider putting in legislation to ban flavors, but within the EU it really hasn't begun to become a topic as of yet. So there is regulation around the flavors, but because they have been approved for use in foods, there is sort of this impression that they should be okay for other uses. But of course, there's just a lack of understanding that these particular compounds are being heated to very high temperatures and being inhaled into the lungs rather than maybe put into your hard-boiled sweets.
Yeah. Gosh. Thanks for that. Owen, you have a question?
Thank you very much, Donald, for that talk. I guess just from just a personal point. So if we have friends who use vaping, we should be saying don't use the flavors, and obviously quit it if you can at all. Quit, but don't use the one with the flavors at all. They're not safe. That
would be my advice. But you have to. So this is where it heads into a complicated public health debate. If your friends are addicted to nicotine and tobacco smoking, you have to weigh up which one is worse.
Yeah.
And there's nothing worse than tobacco smoking. Okay. So if they are not tobacco smokers, or they're not going to revert to tobacco smoking, they most certainly should not vape. There is nothing good about it whatsoever.
Yeah. So flavor, but otherwise go with the ones with no flavors until you can quit.
Yeah.
And then, is there a similar question about like we put perfumes on our skin, and we say a lot of our sunscreens have perfumes. Could there potentially be problems with photolysis of those compounds that are also leading to problems that we're not aware of yet?
Yes, that would be more localized to the skin, you mean?
Yeah.
Yes. So there is definitely there is reports on different sun creams having issues. But again, it's a difficult one to convey in a public health fashion, but it is what is the risk from the sunscreen and what is the risk from skin cancer. And you have to take into, maybe if you're Irish and pale skinned like we are, you're better off with your sunscreen.
Sure. Yeah. No, I'm just wondering, has anyone actually even done that study to see what is there? Yeah. Are there some of these ones we should be not putting into our sunscreens?
I think there is much better study done on that over the years, and I think many of the ones that would have been of questionable are probably out of the higher end products by now. Okay. So that sort of sunscreen is not what we would say a new sort of technology, but the use of these flavors really has only emerged since maybe the from 2010 onwards, and in Europe maybe from 2014 onwards, in terms of them being widely used. They were around, but it has only really grown very quickly because it's shifted into a younger demographic where it's now popular with school kids, essentially.
Yeah. Okay. Thanks, Donald.
Okay, I'm checking the participants and chat for any further questions. I don't see any, and it's Friday, so all these things are perhaps linked. So just to finish up, really, I want to thank all of the 7 speakers this afternoon. It's been it has been a highlight of organic chemistry in Ireland. So thanks to Anita, to Peter, to Owen, to Pete, to Stefan, Joanna and Donal for really 7 excellent talks. I hope those who've attended, and there were 285 registered. At our peak, we're about 120. So I hope those both who attended from within Ireland and also across Europe that they enjoyed the day. And this has been recorded and it will be put up on the Division of Organic Chemistry website. And actually the Italian one has already had over 600 views on YouTube. So you may well become YouTube stars without knowing it. So fingers crossed for that. So thanks again for all the speakers. Thanks to attendees. Thanks for the questions. Have a lovely weekend, and we'll just pause at that. So thanks very much. Bye, everybody.
Bye. Thanks, Pat.